Do we start the? Thanks. Okay, let me start sharing my screen. Okay, get started. Thank you everyone for joining. On behalf of the co-chairs, myself, Samantha Stevenson, Ranfeng, we welcome you to the 2025 Paleoclimate Working Group meeting. By joining this meeting, you agree to our code of conduct, so offer constructive feedback during this meeting, share the air, show appreciation, acknowledge teamwork, listen to understand, communicate context, value new ideas, encourage innovation. So we have 13 talks today, and each has 20 minutes, and including Q&A. So you will receive a reminder at 13th minute. So please wrap up at that point in 2 minutes. So hopefully we can have 5 minutes.
Recording in progress.
For some in-depth discussion. For virtual participants, you can present from your computer, and if you have uploaded your slides, we will have a copy as a backup. We can present from the room for you if you like. And during the Q&A, virtual participants, you can use the raise hand function. And for in-person participants, you can raise your hand. And before you ask your question, please introduce yourself so the online folks know who's speaking. And we have a lunch at 12 at noon. And we have 2 breaks, one in the morning, one in the afternoon. And for people who are interested, please join us happy hour after the meeting at Southern Sun. We can carpool to there. Okay, that's about what I want to say. I will stop sharing. And our first speaker is Qing Wen. Qing is joining us from Nanjing Normal University. So Qing, please take it away.
Hello, everyone. Yeah. Thank you for the opportunity. And today I want to, okay, can you see the maximum screen?
Yeah, that's good.
Okay, yeah. Today I want to share our recent work about the contrasting response of Indian summer monsoon rainfall and the Arabian Sea upwelling to orbital forcing. And this work is collaborated with Professor Zheng Yu from Ohio State University and Stephen from Brown University. At the orbital scale, the most important external forcing is the orbital parameters, like the eccentricity, the obliquity, and the precision. And in the low latitude climate, like the monsoon, the most important driver is the precision. So the most monsoon records exhibit the precision phenomena. And in precision minimum compared with the precision maximum, the perihelion occurs at the boreal summer and the aphelion occurs at the boreal winter. And in contrast, in precision maximum, the perihelion occurs at the boreal winter, but the aphelion occurs at the boreal summer. So in P min compared with the P max, the northern hemisphere summer receives more insolation, but in winter it loses insolation. So this drives the monsoon climate change. But there is a debate as for the orbital scale Asian summer monsoon. First, the Kurzbach first used the general circulation model and simulate the monsoon climate at Likey and PI. And these two periods corresponds to the Pmin and Pmax. And he found that in Nike, the Afro-Asian continent gets warmer and the monsoon rainfall is stronger. So he concludes that the northern hemisphere summer insolation drives the Asian summer monsoon by changing the Latin thermal contrast. And his conclusion is highly consistent with the lake level proxies from North Africa at that time. However, the subsequent Arabian Sea upwelling proxies have another point of view. The peak Indian summer monsoon intensity lacks the northern hemisphere summer insolation for 120 degrees in precision band. It falls more closer to the southern hemisphere summer insolation. And in the obliquity band, it also falls closer to the southern hemisphere summer insolation, because at this band, the northern and the southern summer insolation occurs synchronously. So based on this phenomena, claims that the southern hemisphere summer insolation drives the Afro-Asian summer monsoon, because when the insolation is high, the more moisture evaporated and enter the atmosphere, and this extra moisture will transport northward along the southwesterly monsoon wind, and this will make the land low pressure more stronger, and the monsoon rainfall more stronger. So this is another point of view as for the driving mechanism for Asian summer monsoon. About 10 years later, new records from the Hulu Cave clearly support the Kurzbach's hypothesis. The Hulu Cave actually is very close to our university. Professor Wang in our department, based on the absolute dated and high resolution spatial ozone oxygen isotope records, and shows that the Asian summer monsoon involves closely to the northern hemisphere summer insolation, manifested as the colored and the gray lines here. So here is a puzzling problem. What is the driving mechanism for the Asian summer monsoon at orbital scale? And if the northern hemisphere summer insolation is responsible for the Asian summer monsoon, and why the Arabian Sea records have another type of features? So in order to solve these issues, we use our CESM model, and we first conduct two simulations in 11K and PI, and these two periods corresponds to the precision minimum and the precision maximum time. And we further conduct the sensitive experiments. Then we divide the insolation from the 11K into 4 latitude bands. That is the northern and the southern hemisphere, high latitude and low latitude. And we try to quantify the dominant source for the Asian summer monsoon variations at orbital scale. Yeah, it surprisingly shows that the monsoon climate is largely additive to the regional forcings. The first row is the monsoon climate on response under the global forcing. That is surface air temperature and precipitation and wind, as well as the moist static energy. And the second row is the sum of response from the 4 regional forcings. And we can see the 2 rows have very similar pattern, and with the pattern correlation coefficient extending to 0.9. So this makes us possible to quantify the dominant source for the summer monsoon change. And our conclusion is very clear that the insulation from the northern hemisphere low latitude drives the Asian summer monsoon change that is very close to that under the global forcing, and with the highest correlation of 0.88. And this pattern correlation is actually very much higher than the response from the other three regional forcings. So based on our sensitive experiments, we clearly support Kutzbach's hypothesis that the northern hemisphere summer insolation drives the Asian summer monsoon. And another problem is why the proxies from Arabian Sea upwelling have another type of features. And in order to solve this problem, and we use the CESM, but we incorporated with isotope, so we can directly compare it with the splitting ozone oxygen records. And in order to analyze the phase, we simulate the climate during the past 300 kiloyears. And we use the 100-year acceleration scheme as is widely used in previous simulations. And this scheme is friendly to the monsoon climate at the surface ocean analysis. And this is the data model comparison. In the outer, this is the phase wheel. The outer circle is for the observations, and the inner circle is for our simulations. And in observations, the Indian summer monsoon rainfall and the oxygen isotope is in phase with the northern hemisphere summer insolation, both in precision and obliquity band. And we do simulate this phenomena manifested by the dashed and the red arrows, as well as the orange dots. However, the RBC upwelling records have a changing relationship in these two bands. In the precision band, it largely lacks the northern hemisphere summer insolation, but in the obliquity band, it is almost in phase with the northern hemisphere summer insolation. And this feature is also simulated by our results, but we admit that there is indeed a phase difference between our simulations and observations. Please see here at the dashed and the solid blue arrows. And this may be due to the lack of ice sheet and the greenhouse gases. And we try to fix this problem recently by considering more the full forcing. But at least we have simulated the changing relationship between the Arabian Sea upwelling and the northern hemisphere summer insolation in precision and obliquity band. First, we show the composite analysis in P-min compared with the P-max. We can see the Asian continent gets warmer and the rainfall is much stronger, as shown by the counters, and also with the depleted oxygen isotope, as shown by the shadings. This is also occur in Omax compared with Con-min, with O-min. And our previous findings have shown that the precipitation change is dominated by the northern hemisphere summer insolation. So our following focus will shift to the Arabian Sea upwelling. And this is the correlation map of upwelling to the northern hemisphere summer insolation. We can see that in the precision band, the western Arabian Sea have a negative correlation, but in the obliquity band, here is a positive correlation. This is consistent with the phase wheel that in the precision band, the records largely lacks the northern hemisphere summer insolation, but in the band, they are almost in phase changes. And we try to link the changing relationship of the Arabian Sea upwelling to the Indian summer monsoon wind. And theoretically, the Arabian Sea upwelling is or the surface upwelling is dominated by the wind stress current, and we call it Eichmann pumping. In the Western Arabian Sea, it is located in the west side of the position of the low-level jet. The position of the low-level jet is defined as the maximum wind speed in the surface. So in the west side of it, the wind stress current is positive. So the Eichmann pumping and the upwelling is positive. The upward motion may bring the nutrient water below, and so this is consistent with the high productivity concentrations here. And the Eichmann, the course, this figure shows the correlation map of the upwelling and the Eichmann pumping, and we can clearly show that they are very similar. For example, the precision band here is elective, and Eichmann pumping here is also elective. And for the obliquity band, the upwelling is a positive correlation. For the Eichmann pumping is also correlative, a positive correlation. So this confirms that the upwelling change is driven by the Eichmann pumping change. And the Eichmann
2 minutes.
pumping, okay. The Eichmann pumping is determined by the wind shear and the curvature, and the analysis shows that at orbital scale, the Eichmann pumping is dominated by the wind shear component. So that means the upwelling and Eichmann pumping is determined by the migration of the wind system. So we plot the position of the low-level jet, and in P-min compared with the P-max, we can see that the low-level jet shifts northward a lot, and this may contract the upwelling region in its west side and leading to the anomalous downwelling here. However, in the O-max compared with the O-min, although the low-level jet also shifts northward, but the extent is very slight. So wind speed dominance over the structure and make the upwelling is also positive. So based on our results, our CSM can simulate the monsoon rainfall, oxygen isotope, and upwelling that is largely consistent with observations. And the Asian summer monsoon is largely driven by the local insolation. The Arabian Sea upwelling reflects the position of LFG instead of Indian summer monsoon. And the details of this presentation can be found in our recent published papers. So that is my presentation, and yeah, for looking forward to your questions.
Thank you. We have 4 minutes for questions. Any questions? Betty.
So I'll ask a question. Betty Otto-Bliesner here at NCAR. When you looked at the Asian summer monsoon and kind of the correlations between Southern Hemisphere and Northern Hemisphere precession, did you do the adjustment for the length of the months and seasons? It could be really important. They change with precession in particular for the Southern Hemisphere, not as much for the Northern Hemisphere.
Yes, we have correct the calendar effect before we do the phase wheel. And actually, the results show here is after the calendar effect correct. So yeah, actually the calendar effect do not affect much of the summer monsoon, it may put more effect on the autumn or winter climate response. Yeah, our analysis the conclusion is that.
Thank you.
Thanks.
We have time for more questions. If not, I'm going to ask one. It's a very simple question. So, I think your set of experiments, you prescribe local insolation forcing is super unique and interesting. I'm wondering, you start from pre-industrial and then you look at 11 Ka. In that case, you basically are warming the northern hemisphere during, as seen here, May to July. I'm wondering whether this is like symmetrical. So if you start from a different climate, for example, not pre-industrial, this could be a cold climate. If you impose this localized forcing, should we expect any asymmetrical response?
And actually, for our experiments, we didn't change the CO2 concentration. And if we put the CO2, a different CO2 concentration, maybe it will affect the results, but I am not sure, because in the precision band, actually the peak CO2 occurs almost in phase with the peak northern hemisphere summer insolation. So yeah, I don't know what is the CO2 effect now. Yeah, but actually this is our next work.
That's a good point. Thank you.
Yeah, thank you.
If we don't have more questions, thank you, Qing, for your excellent talk. Let's move on to our next talk from Irina Thaler. Irina is joining us from University of Copenhagen. Please start your screen sharing.
Yeah. Can you see my screen? Yeah.
Yeah.
Can you hear me?
Yes.
Okay. So my name is Irina Thaler. I'm a postdoc with Christian Bjørum at the University of Copenhagen. And well, this is an ongoing project. It is about aerosols in Earth history in general, but more specifically about how the evolution of plants influenced the Earth's climate, or actually if they did. And so what my boss is mainly interested in is the time period between 500 to 400 million years ago, when the greening of both land and oceans by plants and algae happened. And the idea is that during that time, more biogenic aerosols were emitted into the atmosphere. And the question is, did that also contribute to several climate events which happened at that time? For example, one glaciation event which happened at the end of the Eurovision. Okay, what we know, or you probably all know, that aerosols are also important for important agents in the current climate discussion. Like they have a large cooling effect, but on the same hand, they have there is a large uncertainty on their contribution. So they have the largest error bar compared to other agents in the effective radiative forcing. And So what do aerosols actually do? Like, well, they scatter and absorb sunlight, and that leads to a cooling effect on the surface. And if you have more aerosols in an existing cloud, the cloud albedo becomes higher. So that also means that there's less radiation reaching the surface. And additionally to that, if you have more aerosols, it takes more time for the existing water content to condense on all the aerosols, and that's why precipitation is suppressed. Okay, fine. So what causes then the uncertainty? Well, the problem is that aerosols are very heterogeneous in space, time, and composition, and also in their size distribution. That is true for the current climate, and that must be even more true for paleoclimate. And the next thing is that the aerosols, their properties change in microscopic processes, but those microscopic processes then influence like macroscopic things like clouds and maybe then the Earth's radiative budget. And there is an poor knowledge of aerosols in historical and past climate conditions and how these processes evolved over time. And that also then means, since we have a lack of observations in the past, that the current aerosol emission models were calibrated using current observations and then applied to past climates. Yeah, as I said, the emissions were probably not constant over time. And that means we possibly should take their radiative impact into account, also in paleoclimate modeling. Okay, so the aerosol sources for current for the present day climate is such that about half of the aerosols, they come from primary emissions, like sea salt, mineral dust, carbon, while the other half comes from condensing vapors. So that vapors can be inorganic or organic, and those vapors first have to nucleate, like form small molecular clusters, and then grow to sizes where they can become cloud condensation nuclei, which is at the size between 50 to 100 nanometers. And now the question is if the secondary organic aerosols, which contribute to this whole mixture of total amount of aerosols in the atmosphere, changed significantly in the past, such that they influence climate. Okay, so what we did is we used CAMP6 so the atmospheric component of the CSM, and it includes aerosol primary emissions, but also precursor emissions like biomass burning, plant emissions, also DMS emissions from the oceans, volcanoes, sea salt, and dust. And we then took like a standard emission scenario starting from 1850. We switched off all the anthropogenic forces, and then we took that as the reference runs for like a pre-industrial world. And then we scaled down the source strength of biogenic emissions from plants, wildfires, and also from DMS emitted from the oceans to 50% or to 10%. And we also filtered out the contributions from volcanic eruptions. Then we calculated the effective radiative forcing according to the method of CAN 2013. Okay, so what you can see here is like the global average of the, on the left-hand side, you can see the global average of, of the cloud condensation nuclei variation with varying pre-industrial natural aerosol source strength. If you focus on the blue line, that means if you see that point, that means that if you are at 10% biogenic source strength, that the present day cloud condensation nuclei are 80% or 90% higher than back then. actually not present day, but pre-industrial. So we compare it always to pre-industrial. So 80 to 90% more cloud condensation nuclei in pre-industrial times compared to the times where there were no plants, basically. And the other colors, maybe we should not spend too much time on that, but if you look at the orange curve, for example, or the green curve, this just takes into account that an additional variation of primary emissions like sea salt and dust. So the orange curve is sea salt and dust double, and the green curve is sea salt and dust halved. So it just shows like a small parameter space exploration. So whatever I say about biogenic aerosols, of course, it depends on the variation of the other or the contribution from the primary emissions as well, and these are very uncertain. But if you assume that the primary aerosol emissions were the same as in pre-industrial times, and only the biogenic ones would vary, then then the blue curve gives you the results. And on the right-hand side, you then see the change in effective radiative forcing, the total change, so the change from the direct aerosol radiation interactions and the aerosol cloud interactions. So that means that in pre-industrial times, the radiative effective forcing was -4 watt per square meters compared to the pre-plant world. Of course, again, given that the primary emissions didn't change, or they were the same as in the pre-plant world, that means like a large cooling effect of the inclusion of biogenic aerosols. Okay, if we look at it in more detail, on the top you can see that during the pre-plant times, the number of cloud condensation nuclei was mostly decreased over the continents, which makes sense because that's where the plants and the wildfires located. And that the variation actually, so on the right-hand side, you can see like a zonal plot of the seasonal variations for the two different, like for the pre-industrial and for the pre-plant in red, pre-industrial in blue. Yeah, so variations occur both in winter and in summer. And so what I said about the effective radiative forcing before, the largest contribution actually comes from aerosol cloud interaction. It's similar as in the present day climate. And that then can be seen that the low level cloud cover changes a lot, also mostly over the continents and maybe more over the mid latitudes. Yeah. And yeah, the effective radiative forcing due to cloud, aerosol cloud interactions then mostly contributes in the mid latitudes and mostly in the summer months. Okay. Yeah, that also translates into like the pre-industrial world has been like locally up to 2 degrees cooler in some spots over the continent compared to this pre-plant world I was talking about before. And yeah, and that also affected the precipitation, like for the large scale precipitation, there is no clear pattern seen, like it looks a little bit messy. But for the convective precipitation, there is a clear pattern. So, so there is an increase of convective precipitation rate in the pre-plant world compared to the present day world in the northern hemisphere mid latitudes. Okay. Maybe I went a bit fast. Okay, so the conclusions. So the greening of the Earth might have had a large climate impact, but of course the realism of our experiment is limited. The list of limitations could be very long. Like, first of all, we use like only the atmospheric component of CSM and present day continents and present day atmospheric circulation. But however, the aerosol transport and source distribution was very different than 450 million years ago. Furthermore, it's well known that the climate sensitivity of the CSM is very high, and that therefore these results are probably overestimating the effect. And furthermore, we also know that, or actually, it's a large uncertainty as well, that we don't know the primary emission background, and therefore the overall effect of the biogenic aerosols, which will also depend on sea salt and dust variations, which are currently not really known. And so the outlook would be that the next step we want to use like paleogeography and use the fully covered CSM to take into account like atmospheric and ocean feedback effects, as well as the effect from vegetation. And we also didn't change the CO2 levels so far in the model. So that would be, again, a thing to do. And then to scan several time slices over this period where the vegetation onset or greening happened, and see how well we can, with these simulations, then reproduce the climate back then. Thank you very much.
Thank you for the interesting talk and the great timing as well. Any questions? We got one question from Ran.
Hi, Rena. This is Ran. This is a very interesting talk. It's always fascinating. It's always fascinating to think about how like plants evolution can change the climate. I was wondering, well, you focused on land plant, but do you know what happens to the phytoplankton?
Actually, we did take into account the DMS. Because the phytoplankton produces the DMS, and the DMS is then leading to more sulfuric acid in the atmosphere, right? And that sulfuric acid then leads to like more nucleated particles. So we did also vary the DMS source strength. But I didn't go into detail in the plots, but there was also one of those colored lines actually showed like the DMS variation only, and we didn't. So in that run, we didn't actually take into account the plants or the land plants, and it didn't have a very large effect. Let's say, like in our case, the dominant effect I think comes from wildfires, not per se from the plant emissions as such, but more from wildfires. And so the ocean effects are not large.
Right. I was wondering, so do you know anything? Well, the DMS you varied is from pre-industrial conditions.
Sorry,
I was wondering, do you know anything about like phytoplankton evolution at the time, or something that might be very different from what we know about present day?
So apparently there was a transition between like green algae and red algae, and the fraction of those varied. And so there was, so that's why it was a good assumption to think that actually the DMS production went up. because now I'm not sure if it was the green or the red algae, which ones produced less TMS, but so there was time evolution in the ratio of those algae present in the oceans, and that caused over time the increase of TMS. At least that's as far as I know.
Thank you. Very interesting.
We very
More questions? Okay, one more.
I'm Han Chen Song, and I'm a PhD student in China University of Geosciences, and I'm visiting INCA here. I have a simple question: what is the most important factors of the aerosol distribution in very deep time, volcanic or continent distribution? What do you think about this? Thank you.
Aerosol distribution in what?
In
like
very
spatial
in deep
distribution in deep time. Okay. I think the deep time conditions can not be like I'm not an expert myself in paleoclimate, but
Oops.
Arina, we lost your audio.
Can you hear me?
Oh, yeah, we can hear you now.
So there had been large variations of short timescales that can have happened from wildfires, like factor of 10 variation, and we only I played around only with a factor of 2 in sea salt, for example, or dust. I think so. Volcanoes, of course, are very important. So I think that that it can actually not be said as such general statement what was the most important source. I think it varied, and that's why it's very important that for each time period you want to model, you actually try to constrain aerosol emissions within that time period, even though it's not easy to do that.
Okay, so it's really complex.
Yeah, I think so. Yeah.
Thank you.
Okay, thank you, Arina. Let's move on to our next talk from Shixiong Hu. Shixiong is joining us from University of Connecticut.
Hello, everyone. Can everyone hear me?
Yeah.
Hold on. I'm going to present my slides. Can everyone see my slides?
Yes.
Yeah. So hi, everyone. I'm Shixiong Hu. Oh,
Wait a minute. We are. Can you swap the display?
swap the what?
Oh, we are looking at the presenter view. Yeah.
Oh, okay. Sorry. Hi, everyone. I'm Shixiong Hu from University of Connecticut. I'm a PhD candidate. So I'm working with my advisor, Clay Tabor, and my collaborator, Chuck Spadian, on this project. So today I'm going to present our proposed simulations on addressing the soot emission uncertainties at the KPB boundary. So here's a little background. So we are looking at the Cretaceous Paleogene mass extinction event that's coincident with the well-known 10-kilometer kill dinosaur asteroid that's 66 million years ago. So on the one hand, from the proxy perspective, well, previous sedimentological records shows that the soot deposition is contemporary with the iridium deposition across the boundary at the crater. On the other hand, there are a lot of previous modeling work suggesting that the massive soot injection at the KBB that leads to the global extreme cooling, light reduction, and precipitation reduction. However, still in the community, there are lots of debates and controversy over the topic of the source of the soot. That means that, well, where are the source actually originates? Is it from the impact or from the fire or a combination? So we don't know actually. So here's the kind of a definition of the source in our simulations, in our research. So we assume the soot either from the fire or from the impact itself. So if the soot originates from fires, well, we emit them at the tropopause over vegetated regions. And the fire-generated soot consists of coarse soot and fine soot. The coarse soot has a larger size than the fine soot. It only stays in the atmosphere for 2 days or 3 days. So you can imagine that it doesn't have any effect on the climate. However, it has a huge impact on the deposition itself. So that's why we're looking at sedimentological records. On the other hand, the fine soots will be emitted ballistically at 50 kilometers. That we assume that it only originates from the impact. So it doesn't have the coarse soot. So in a nutshell, well, coarse soot only exists when the fire happened. So the goal of this research is to explore the various uncertainties, include the emission timing. Let's say when will the emission will be starts, and emission duration, and when and how much should we emit the soot is at the tropopause or surface. Additionally, the uncertainties also includes the size of the coarse soot. Since this is a wide range of wildfires that actually differs a lot from the present day wildfires. So the methodology is that we are looking at by comparing with our model simulations with sedimentological records. Well, apart from that, we also explore the climatic responses to address the uncertainty of the source of the soot. So here's a modeling setup and a methodology. So we use the CESM 2.1.3. So for the atmosphere component, we're using the WACOM 4 is a high top atmosphere model with interactive chemistry module coupled with CARMA aerosol model, a sectional aerosol model that allows the aerosol to calculate growth and sedimentations. So for the boundary conditions, we're using the Cretaceous Paleogene reconstruction boundary conditions. That includes the paleogeography, paleotopography, the greenhouse gases levels, and reconstructed vegetation's fractions, and the reduced solar constant. So in the CARMA aerosol model, we are capable of injecting various of aerosols that includes the sulfur dioxide, that includes the soot and dust and various gases. But here we are specifically looking at the soot and water vapor injections from the asteroid impact. So that's the model setup. So for the proxies and sedimentological records, so we were looking at the soot abundance and the soot fraction records at 12 sites across the KBB, based on a previous work from Warbeck's work back in the 1980s and 1990s. So here is a table for the proxy data sets we are using. So the first column in this table is the name of the sites, and the second column is the total carbon deposition. The number on the left is the result of the total carbon deposition. The number on the right is the range of the error bars. And the third column is the fine soot ratio in percentage. So you might have noticed that, well, there's no error bar provided in the fine soot ratio. That's simply because that is missing in Warbeck's previous work. So in the following part of my presentation, I will mainly focusing on discussing the total carbon deposition here. So here in the table below, in red circle here, well, is the process data. So here are a few things we did to process the raw data. So first of all, we averaged 3 sites in New Zealand. That is because, well, they are at the same grid cell in our model, because our model is 2 degrees in atmosphere and 1 degree in the ocean. And secondly, we removed 3 sites that includes August, Rotten, and Alien Carbon. These 3 sites are removed because the sample processing technique involved might lead to the loss of a carbon in the samples. So we have private email communication with Dr. Wendy Warbeck over this issue, and she agreed that the removal of these 3 sites are reasonable. So next, so we run 11 perturbation rounds in total, but here I'm So next section, I'm going to present each of the uncertainties that we're trying to address by showing each of the comparisons of the cases one by one. So before running the perturbation runs that have the certain injections, so we run a CAM4 only case with 4,000 years spin-up climate until the climate reaching equilibrium. Then we switch to a Welcome 4 spin-up case for another 100 years until the chemistry and climate reaching equilibrium. So that's kind of the prerequisites before running this perturbation run. So first of all, we are looking at the fine soot fraction. So that simply means that the percentage of the fine soot in the total element soot. So this figure on the right here, well, the y-axis is the model simulated results. The x-axis is the proxy records results. So you can see that the error bars here shows the range of the uncertainties that's in Warbeck's records. So there are two numbers we're applying here. The 26.6% of the fine soot here is the mean of all the sites from the table I just showed. And the 11% is the minimum of the fine soot fraction among all sites. So from the results we're showing here, well, these two cases shows a pretty close performance when they are comparing with Warbeck's records. So it's very hard to tell, like, is it like the 11% is better or 26% is absolutely better than the other? No. So statistically speaking, the 26.6% has the highest correlation comparing with the Warbeck's records. So we can say that 26.6% is better based on our comparison showing here. So as you can see, well, as I said, there's no error bar provided in the fine soot ratio here. So it's very hard to tell, like for each of the sites, well, is our model simulations within the range of the error bars provided in terms of the Warbeck's records? So we don't know. So it's very hard to tell. Secondly, another uncertainty we're trying to address is the emission amount. So this comes from the debate that whether the wildfires triggered by the impact is global or not. Whether it will be global or not will directly determine how much should we emit. So here we apply two emission numbers here. The first number is the 72,000 teragram of the total element soot. This is based on Warbeck's previous papers and sedimentological records. The other number is based on our simple calculation. So we assume that all the vegetations in our land model will be burned. So that's just a purely numerical calculation. So based on our results showing here, well, if we assume that all the vegetation in our simulations gets burned, it has an overestimation overall. So it means that it's unrealistic is an unrealistic assumption, especially at the sites in the Stevens client. So is a site in Denmark near the coast. It has a pretty high overestimation. So further, we also wonder how long will the fire will last. That means that how long will the emission will last. So we don't know. So there is very little research over this topic. How long should fire be burned? Is it over several weeks or months? So we don't know. So here I'm specifically looking at the extension of the duration from 1 day to 2 weeks. So we found that most of the cases, they are at most of the sites in both cases, well, all the numbers are within the range of error bar and they shows a pretty close correlation with each other. So that means that, well, the emission duration possibly don't play a role here. So another hot topic in the uncertainty is the seasonal timing. So there are a couple of recent papers that based on the fish and birds fossils at the KBB that found that they conclude that, well, the impact at the extinction might be ranging from late spring to early summer. So here we picked 3 months for testing purposes here. It's March, May, July. So we found that the July timing performs the worst, while the May timing seems to be the best estimates we're showing here. So this means that, well, the probably mid-spring or late spring might be that's the May timing might be the most appropriate timing we're showing here. So we're also not sure how much and where should we emit the fine soot? Is it emitting at the tropopause or over the surface? If so, how much or what percentage should we put here? So there are previous paper from my collaborator that emits the fine soots at the tropopause while the coarse soot at surface, but they are only looking at the climatological responses. But here we're looking at the comparison with Waback's records. So we don't know which of them are realistic or not. So we propose 3 experiments here. So in the red points shown in this figure is that we emit fine soot and the coarse soot both at tropopause. In blue points shown in here, we emit 50% of the fine soot at tropopause and 100% of coarse soot at tropopause. And the points in yellow is that we emit coarse soot fully at tropopause and coarse soot completely at the surface. So surprisingly, we found that if we emit coarse soot at surface, well, it has the least correlation compared with Waback's records. That means that although the coarse soot only stays in the atmosphere for 2 days, but still during these 2 days, it will be lofted actually. It will be lofted to the tropopause maybe. So if you're looking at the red points and the blue points, you will find that if we emit coarse soot at the tropopause, they have a higher correlation. And on the other hand, the altered fine soot ratio at the tropopause doesn't seem to play a role here.
2 more minutes.
Okay, another hot topic is that the fine soot and the combined way of fine soot impact soot. So the fire and the impact soot is that we replace the 2,500 teragram of the fire-generated fine soot with the impact soot. So we also find that they have a close correlation with each other. So this means that the way of how they emit the soot probably doesn't play a role. So this is the coarse soot side. This is probably minimum to our purpose here. So due to the time limitation, I will jump from this slide. So here is the geospatial pattern of the total soot deposition. So there are a few things where I'm going to focus here. Is that most of the carbon deposition are focusing on the mid and low latitudes. And you can see that most of the deposition focused on the land regions. That is because most of the total soot consists of the coarse soot, since they only stay in the atmosphere for 2 days. So they were deposits near the source of our emissions. And as you can see in the fine soot ratio I'm showing here, well, most of the fine soots, they can stay in the atmosphere for 2 years. So they can be transported to the ocean. So that's why most of the fine soot deposit in the ocean. So here is the climate responses. So we present several cases. So the conclusion is that we found that, well, the additional case when showing here is the curve in black. That's the impact case. That means that in this case, all the soot originates from the impact. So we found that the impact soot itself is already to trigger the same scale of the climatological responses as the other 2 fire-triggered case. And that's the temporary speaking. But if we are looking at the geospatial pattern, well, surprisingly, they also seems to be matched pretty well. So this is the maximum cooling responses. So you'll find that the scale of the cooling and the geospatial pattern of the cooling are pretty similar. And this is the shortwave radiation reduction in the first year. So you will find that these 3 cases, they have pretty identical responses in scale and the pattern. So the conclusion is that, well, we found that in the model proxy comparison I'm showing here, fires are necessary to have agreement with our geological records. And our best estimate case is that we emit 72,000 teragram of soot on the May the 1st over 1 day with 26.6% of the fine soots, and both of them, coarse and fine soots, will be emitted at tropopause. From the climate perspective, well, we find that, well, the 2,500 teragram of impact soot itself, well, could exert nearly the same climate responses as the much larger fire-driven soot emissions. And I'm ready for questions.
Thank you for the great talk. Do we have questions? Oh, that's a clap.
Oh, that's clap.
Maybe I can ask. Okay, Jan.
Sure. I was curious, Jean, can you say something about the extent of the fire out of curiosity based on your experiment? If it's not, then feel free to say no.
Can you repeat the question? I think
I
you're
was
breaking
curious
up.
the extent of the fire based on your your estimate of
Oh,
amount of carbon burned. Is it
you-
like 2/3 of the vegetation, or just a small amount of vegetation, or
for the vegetations, well, I think our setup is pretty limited, so it's not dynamic at all. So it's just kind of based on previous Cretaceous. So they have a paper in the that have the Cretaceous vegetation set up. So it's not dynamic at all. So it's kind of
no, I
from
was thinking about based on your estimate of teragram of the carbon burn. Right.
yeah.
Can you say something about
Yeah.
like a rough estimate of the amount of material potentially burned on land? And then translate to like potentially maybe like roughly the amount of surface area burned on land. Is it just entire North America, or actually managed to?
It's a globe. So we scaled the emission of the soot by the vegetational fraction across the globe. So we assume that the global vegetation, they're all on fire. So we scaled by the vegetation carbon in the land model component.
Okay, so your estimate would suggest that everywhere it's on fire.
Yeah, exactly.
Oh, okay, great, thank you.
Sophia?
Oh yeah, just quickly ask, thinking about the Wallback records of that you're kind of using to infer soot. Where are those records coming from? Are they primarily terrestrial records? Are there any other kinds of records in there? Is there kind of a spatial bias in the records?
Yes. So we have 12 sites in total. So yeah, we have 12 sites in total. So except the DSDP 465, the other 11 sites, they are in the shallow marine near the coast. So they are distributed across the globe. That includes Mediterranean areas, and also the additional sites is DSTP 465 is located in the Central Pacific, and they have, so it's across the globe from 12 sites based on Wallback's previous work in the 90s. So I don't think there are additional sites we can make use of. So yeah.
Okay, great.
Maybe we can take one more quick question. Oh, please go ahead.
Hi, my name is Daphne, and I wanted to ask if, because you're saying that there is a spatial distribution of these sites, can you not try and compare specific areas from the model, or average a specific area and then compare that to the closest site?
You mean looking at I think the scatter plot here is kind of thing we did. So you can see in the y-axis, the y coordinates of each of the points stands for the model simulation. So that's actually from our model simulations near the sites.
Okay.
Yeah.
Okay. And do you see any large difference between the sites, or do you see them constant?
Yes.
But you said that you were assuming that fire is everywhere, right?
Yeah.
But is it the same scale? Is it different between sites? Do you see difference between hemispheres, or?
Not hemisphere, but we do see kind of like overestimation in the Stebbins client. So you can see that we found that in every case we run, Stebbins client has like 50% of overestimation of that. So we have very limited sites in total. So that's 7 sites in total after removal. And that one singular size of overestimation has already leads to our low correlation in our model and proxy assessment. So we're trying to fix that, but let's see how it goes. Yeah.
Okay, thank you. Good luck.
Thank you, Daphne, for the question. And in the interest of time, let's move on to our next talk from Xiang Li. Xiang is joining us from Duke University.
Hi, everyone. My name is Xiang Li. Today, I'm going to talk about persistently active El Niño Southern Oscillation since the Mesozoic. I'd appreciate input from my co-authors, Professor Shinen Hu at Duke University, Professor Yongyun Hu at Peking University, Professor Wenju Cai at Ocean University of China, and many other co-authors. So ENSO is a defining mode of interannual climate variability with profound impact on global climate and ecosystems. Although ongoing efforts have offered insights into how ENSO will change in the future under anthropogenic warming, the geological history of ENSO remains intricate. Available geological evidence suggests that ENSO might have been active as far back as the late Cretaceous, indicating that ENSO variability may have been a salient feature of the Earth's climate system for tens of millions of years. This slide shows how the Pacific Ocean evolves from 250 million years ago to the pre-industrial with an interval of 10 million years. Due to tectonic dynamics, modern global oceans are originated from the huge Panthalassa Ocean 250 million years ago. Given the vast change of the Pacific Ocean and that ENSO is a climate variability based on the climate mean state, our questions are, in the past 250 million years, how does equatorial sea surface temperature change? Does ENSO remain active? To address these questions, we performed 26 time-slice climate simulations for the past 250 million years using CESM 1.2.2 with a fully coupled configuration, and the resolution is T31G37. The ocean model has a nominal 3D grid, and in the meridional direction, the grid is about 0.3 degree at the equator. So this animation shows the paleogeography that we used for each climate simulation every 10 million years. And for atmospheric CO2 concentration, instead of using the reconstructed value from proxy data, we take an alternative approach. So what we did is based on the reconstructed global mean surface temperature, as shown by the black asterisks shown here in the bottom panel, and by tuning the atmospheric CO2 concentration for each simulation, we made so that the equilibrium global mean surface temperature simulated by each simulation is consistent with the reconstructed value. So as you can see, our simulation result, as shown by the black line, is quite consistent with the reconstructed value. And the global mean surface temperature in the past 250 million years generally shows a cooling trend ranging from 26 degrees Celsius to about 10 degrees Celsius in the pre-industrial. And for the solar constant, we follow that of Gulf 1981. So to set a linear increase across simulations, and for the period 250 million years ago, the solar constant is set about 98% of the present day value. Let's first see how mean state equatorial SST and zonal surface wind change in the past 250 million years. The shading shows the SST and the contour shows the zonal surface wind, with dashed line shows the easterly trade. As you can see, there is robust warm pool cold time system with overlying easterly trades. And further, we investigate the ENSO variability as shown this figure, which is the time variation is in equatorial SST interannual variability, defined as the standard deviation of SST anomaly, which shows there is the strongest equatorial SST interannual variability is always located in the eastern equatorial Pacific around 120° west, which means that there is persistently active ENSO in the past 250 million years. As also can see in the map, different period have different amplitude of ENSO. So here we define the amplitude of ENSO as the standard deviation of area averaged SST anomalies in the eastern equatorial Pacific, as shown by the green box here, which is the ENSO box, where there's the strongest SST variability. As shown by the black line, ENSO amplitude varies by a factor of 2 across 26 simulations, ranging from the weakest 0.6 degrees Celsius for the pre-industrial to the strongest 1.3 degrees Celsius at 150 million years ago. And interestingly, we find that although all the past warm climate simulated here although they are warmer than the relatively cold pre-industrial, but there is no obvious relation between ENSO amplitude and global mean surface temperature. For example, the largest ENSO happens in 150 million years ago. However, the global mean surface temperature is only around the median over the past 250 million years. And also, there is no correlation between ENSO amplitude and the zonal SST gradient. So in order to investigate the mechanisms controlling the variations of ENSO amplitude, we use the BJ index or Bjerknes linear stability index to measure the ENSO's growth rate, which can be decomposed into two negative feedbacks, thermodynamic damping, and three positive feedbacks, zonal advective feedback, Ekman-Appwelling feedback, and thermocline feedback. We show that the BJ index is highly resembles that of the ENSO amplitude with a significant correlation of 0.76, which suggests that BJ index can captures about 57% of the variations in ENSO amplitude. And generally, a larger BJ index will correspond to a greater ENSO amplitude, and vice versa. Among the five contributing processes, it's found that the zonal advective feedback and the thermocline feedback, as shown by the blue and the yellow curve, is the most important factors compared with other three contributing factors. The zonal advective feedback means that when assuming there is a positive sea surface temperature anomaly in the eastern equatorial Pacific, it will induce eastward surface wind forcing, and which will drive eastward zonal current anomaly to further enhance the initial warming. And the thermocline feedback means that also similarly, there is a positive SSE anomaly. There will be eastward wind stress, and it will induce deeper than normal thermocline anomaly in the eastern equatorial Pacific, which will cause an anomalously warm subsurface water. And through the effect of mean upwelling, it will further feed back to the surface to enhance the initial sea surface temperature warming. And our further analysis shows that the processes of beta U and beta H controls the zonal advective feedback and the thermocline feedback respectively. So the beta U means the sensitivity of zonal ocean current to surface wind, and the beta H means the zonal tilt of the equatorial Pacific thermocline to the wind forcing. So in the next slide, I'm going to show that the change in beta U is linked with that of beta H. As shown in this figure, there is a local maximum response of positive thermocline anomaly in the eastern equatorial Pacific to an eastward equatorial surface wind forcing, which means beta H. So we start with beta H. And this local maximum will mathematically give rise to a negative second meridional derivative of thermocline anomaly. And further, it will lead to a positive, in other words, eastward geostrophic component of zonal current anomaly based on a linear reduced gravity model in an equatorial beta plane framework. And as a result, there will be an eastward zonal current anomaly in response to surface wind forcing, which exactly means beta U. And this is because the zonal current anomaly are dominated by the geostrophic component. Therefore, the change in beta U is tightly correlated that in beta H. And the strength of beta H is affected by the background thermocline depth in the western equatorial Pacific, as shown here, with a negative correlation of 0.70, which means that when the background thermocline is deeper, the equatorial thermocline tilt becomes less sensitive to surface wind variations. In other words, a weaker beta H. According to the shallow water theory. And
2 more minutes.
Sure. And therefore, zonal advective feedback and thermocline feedback are weakened, which will ultimately give rise to a weaker ENSO. So consistently, the variations of ENSO amplitude is significantly negatively correlated with the background equatorial thermocline depth. One important limitation to the previous linear stability index is the lack of atmospheric noise. So we compute the atmospheric noise by removing the SST force signals, and we compute the standard deviation of the residue in the central western equatorial Pacific as the atmospheric noise. As shown here, there is a positive correlation between ENSO amplitude and atmospheric noise, which means that stronger atmospheric noise will potentially give rise to a stronger ENSO. And we find that there is almost no correlation between atmospheric noise and BJ index, which means that they serve as two independent factors in controlling the amplitude of ENSO. And the scatters are color-coded here when a larger ENSO amplitude would require both a larger BJ index and a stronger atmospheric noise. So motivated by this, we construct a multivariate linear regression model combining BJ index and noise to predict the ENSO amplitude. So ENSO amplitude predicted by this simple model is highly correlated with the simulated ENSO amplitude with a correlation of 0.87, which means that the BJ index and atmospheric noise together can explain about 76% of the variations in ENSO amplitude. So to wrap up, in this study, a series of 26 coupled climate simulations forced by paleogeography, CO2, and solar radiation in the past 250 million years are performed and analyzed using CSM. And we show that ENSO has been a leading mode of tropical sea surface temperature variability in the past 250 million years, but with different amplitude. Our results uncover the geological history of ENSO from a modeling perspective, and our findings support the importance of changing ocean vertical thermal structure and atmospheric noise in influencing projected future ENSO change and its uncertainty. Please check this paper for further reading. Thanks.
Thank you for the great talk. Do we have questions?
Thank you.
I have a question. Sorry, I don't know how to raise my hand.
Oh, go ahead, Sam.
Okay, great. Yeah, hi, Sam Stevenson here.
Hi.
I guess this is really interesting. I was curious whether you had a big picture understanding of how these feedback changes relate to paleogeography. Like, are epochs where the thermocline feedback is stronger or weaker systematically associated with seaway openings or closings, for instance?
Yeah, it's really a nice question, and but we did examine the relationship between these feedbacks with the different paleogeography features, like as you mentioned the widening of the Pacific Basin or the open or close of the seaway, but unfortunately, there is no obvious relationship between the matrix of the paleogeography change and the ENSO amplitude. And so we only find that we can only relate the change of ENSO amplitude to the change of mean state, that is the thermocline depth.
Thanks. So next, maybe Dayun, you can go ahead and ask your question.
Hi, great talk.
Hi.
I'm a PhD student at the University of Michigan, and I have a question about your CO2 level settings. So you
Yes.
prescribe your CO2 not based on the proxy record, but based on the GMST.
Yes.
Explain a little bit more why you did that, and then also, did you end up seeing any differences based on GMST reconstructed CO2 and then the proxy record you have, or was it similar at the end?
Yes, nice question. So, yeah, actually, our CO2 level used in our model is relatively higher than the proxy data, mainly because two reasons. The first may be related to the climate equilibrium sensitivity of the CSM1 model, which is about 2.9 degrees Celsius. So if the climate so that which is relatively low, so we would use more CO2 to reach the global mean surface temperature. And the second reason is related to the dynamic vegetation model that we used, which actually underestimate the vegetation cover so that the surface albedo will be larger due to the bare ground, so which will cause a cooling effect, so that we need to add more CO2 into the model, so that our CO2 level is relatively higher than proxy data. Yeah, but in this way we can simulate the global mean surface temperature as shown by the reconstructed value. So that's why we use this alternative approach.
Yeah.
Betty, do you want to ask your question?
I guess I could. Betty out of Leisner at NCAR. It's related to Dayan's. I'm looking at your global mean surface temperature, and it looks quite cool in places like the Turonian and that. I would have thought global mean temperature was warmer than about 24 degrees Celsius during that part of the, that's kind of a hothouse climate.
Yeah.
So could you say a little bit more about that? And how it might affect your results, I guess, is more of my question. If it was warmer than what Scotese thinks, or hotter.
Did you mean that around 250 million years ago, the global mean surface temperature is
No, more about 90 million years ago, I would have expected global
90?
mean temperature to be warmer than what Scotese suggests. And I was wondering if it was hotter than what he has, do you think that would affect your ENSO conclusions for that time period?
Oh, so other proxy data may indicate that the temperature is not as high as here shown by Scotese.
I thought it'd be higher, hotter.
Oh, it might be higher. Okay.
Yeah.
Yeah, that's really a good point. So, but actually, in our ENSO result, we didn't find a very tight correlation between ENSO amplitude and the global mean surface temperature. So, the global mean surface temperature may indirectly affect ENSO amplitude. Like the direct way should be the thermocline depth. So I think, yeah, it's really a good point and worth doing like sensitivity tests, like using other reconstructed global mean surface temperature to see if there will it will cause significant difference of our the result.
Thank you.
Thank you. Ran, do you mind put your question in the chat? We are over time now.
Yeah, I'm actually typing it.
Thank you. That's our first morning session, and thank you, everyone. Please come back in 17 minutes. So
Emily Nigro. Emily, please take it away.
Hi, everyone.
So was Ingrid's recorded or not? I hope so.
Great, I can see your slides and hear you.
Never even see this. Okay, great. I'm Emily. I'm a PhD student at Stanford. And I also was at NCAR this past summer working with Sophia and Zhang. And I'm going to talk today about my research on Western US hydroclimate over the last several thousand years, using both proxy reconstruction and CESM simulations. So Western US is an interesting region to study because there's a lot of climate variability. In particular, it's very prone to droughts. Rainfall is very variable. And there's still a lot of uncertainty in how precipitation will change with future warming. So in this plot, we can see that precipitation could plausibly increase or decrease. And some of that is due to natural variability. And there's also a lot of uncertainty in our model. But we want to understand how water supply will be impacted in the future. So we can use the paleoclimate record to test models that we're using for future projections and see how well they are recreating independent proxy samples. So the period that I'm looking at is the Holocene. It's about the last 12,000 years. And here's a few different temperature reconstructions. This is in anomaly space relative to the pre-industrial. So we can see that it was warmer than pre-industrial. Something else happening in the Holocene that is interesting is that there were several global vegetation changes. So we had a green Sahara and also some greening in the high latitudes. And another nice thing about looking at the Holocene is that it's very recent geologic past, so we have a lot of proxy records. So my overall question is, how have the amount, timing, and distribution of precipitation in the Western US changed throughout the Holocene, and how do these different vegetation changes impact the hydroclimate? So to do that, I'm looking at the Community Earth System Model version 1.2, and specifically the isotope-enabled version. And we have these different time slice simulations at 0, 3, 6, and 9,000 years ago. And then at 6 and 9,000 years ago, we have several different simulations that each have a different prescribed vegetation change. Additionally, we have this proxy record from several locations in the Rocky Mountains in the Western US. And so we can use the proxy measurements to sort of assess how well the climate model is reproducing what the proxy says, but we can also use the climate model simulations to better understand the conditions that are producing the proxy measurements. And here's a map showing some of the prescribed vegetation changes in the simulation at 6 and 9,000 years ago. One is the Green Sahara. So we add this shrubs where there used to be bare ground. We also have Green Sahara plus Arctic greening, and then Green Sahara, Arctic, and mid-latitude greening. And the results I'm about to show are focused on the summer, because that's where we saw the biggest differences between simulations. So here we're looking at temperature. This is a regional average, and it's in anomaly space relative to the pre-industrial. So we can see the temperature in general decreased over the Holocene. We can also see the difference between simulations with prescribed vegetation and without. So we see this impact of, in the Western US, when we have a greening, temperature increases, so the summer gets warmer. And interestingly, we see at 6K, there's this bigger gap than at 9Ka between the greened and not greened simulations. For precipitation, we can see that it increases through time, especially from 9 to 6K or from 6 to 3, depending on which simulations we're looking at. And here again, we can see the impact of added vegetation makes the Western US drier. And especially, again, we see at 6Ka, there's a much bigger impact than at 9Ka. So we wanted to understand, what's going on at 6Ka. And because the Green Sahara is responsible for a lot of the change, we looked at mechanisms that might be controlling the Green Sahara and its impact. So here we are looking at upper level velocity potential and diverging winds. So the blue colors on this plot show where air is rising, and the brown shows where air is falling. And so where we have rising air, that might be convection and precipitation, whereas falling air would be drying. So starting with 6Ka, at the top, we're just seeing the effect of the difference in boundary conditions. But then if we look at the bottom plot, we have the impact of the Green Sahara, and we see this big change. So we have over the Sahara, a lot of rising air convection, translating over to subsidence over the Americas, which would likely cause all of the drying that we saw. And Tuwari and others identified a similar mechanism of this same impact of the Green Sahara for like South America and northern Brazil. Here we're seeing that this also matters for the Western US. Then if we look at 9Ka, we're seeing almost the inverse, where it's very sensitive to the boundary conditions, but then the added effect of the Green Sahara is much less. And so we think this is kind of explaining the difference we see at 6Ka and 9Ka. So kind of now I'm going to move on to water isotopes, which present this common unit that we can compare. We can simulate in ICESM and then compare to our proxy measurements. So isotopes are different versions of an element with different masses. So you can think of having light and heavy water or light and heavy oxygen. Because they have different masses, they partition themselves differently in the water cycle. And that can give us information about past temperature and precipitation. And beyond just precipitation amount, we can learn about the moisture source or the trajectory of the precipitation, which is really cool. And we have specifically this delta 18O metric, which represents a ratio of 18O to 16O, so heavy to light. So here is the simulated delta 18O of precipitation in the summer in the Western US. In CESM, it is decreasing through time. Here again, we're seeing at 6K this big spread. And if you remember, this is very similar to the temperature. So we think it's just mirroring what we saw with temperature. But I also have these proxy measurements. So they're a type of iron oxide. And iron oxides are really abundant on Earth, which makes them potentially really useful for paleoclimate reconstruction. And in particular, these samples are called ferrocretes. So here's a picture at the bottom of one of the samples. And these are, we're measuring goethite, which is the mineral. And these are forming in naturally acidic stream drainages in the late fall. And we think that they are representing past summer precipitation. And we, at each of these 3 sites, we have several samples going through time that were previously measured by others in my group. So we have a delta 18O record from these iron oxides. When we plot them on the graph, I did this by binning the samples into the closest time point and then sort of across all locations to get this regional average. But we can see that the delta 18O in our samples is increasing through time. And it's kind of the exact opposite of what's the simulation is showing, which is interesting. The way that this increase in delta 18O is explained is that they think there was an increase in isotopically heavy summer precipitation. But, you know, how do we know that that's the correct interpretation? There are a lot of different processes that could impact delta 18O. We can actually look at the third stable isotope of oxygen, which is oxygen 17. And if we measure all 3 of these isotopes, that gives us a fuller picture of what's going on and helps constrain our interpretation of delta 18O. So we have this metric called cap 17O, capital delta. Sometimes this is called 17O excess. And it's defined sort of graphically as if we have a plot of delta 17O versus delta 18O. These are delta prime, which means it's the linearized version. But we have this plot and we have some expected equilibrium relationship between 17O and 18O, which is this terrestrial fractionation line. But then if we have a non-equilibrium process affecting a sample like evaporation, we will get some displacement from this line. And that vertical displacement is what cap 17O represents. And this is not really affected by temperature. Mainly what is controlling cap 17O is the source environment of the precipitation. So really what we're getting at with this metric is where did our moisture come from? So I remeasured several of these ferrocrete samples last year, and we measured the delta 18O, but also the cap 17O. And so I'm showing you here 3 sample sites. On the far left, we have the Northern Rocky Mountain site, and then the other two are from southwestern Colorado. And the top row is just the Delta 18O showing generally we can see at mostly it is increasing through time at the sample sites. But if we look at the bottom row, CAP 17O, we're seeing, especially in this middle plot, a steady decrease through time. The other two, maybe in the late Holocene, are decreasing. But even just this small decrease in CAP 17O, we think is due to a change in the moisture source rather than some other process. So this is consistent with the interpretation that there's an increase in monsoon summer precipitation. That's this map up here. The summer precipitation sourcing from down here would have a low CAP 17. And so that could explain this decrease. But just sort of to end, in ICESM, we see temperature decrease and precipitation increase throughout the Holocene. And I should say that that is pretty consistent with a lot of other proxy records. But then for Delta 18O, we don't really know what's going on. We see in the simulation decrease, but our proxy record is showing an increase through time. So we have this discrepancy. But we did also see through the different simulations that remote vegetation can have really important impacts on the Western US. And in particular, at 6K, we saw this interesting effect of the Green Sahara that we don't really see at 9Ka, which is that there's a lot of increased convection over the Green Sahara, translating over into subsidence and drying over the Americas. But going forward, I'm going to continue looking at CAP 17. And in particular, I've been working on like a simple vapor transport model to sort of think about what other processes could explain a change in CAP 17O to sort of hopefully support our interpretation of this change in moisture source. And I would also like to, just keep investigating why there's this discrepancy. Is there something in the model? Is it our interpretation of the proxy system? So hopefully we'll be thinking more about that. But yeah, with that, I would just like to acknowledge my collaborators, Sophia and Zhang, and my advisor, Paige at Stanford, and then Dan and several people in his lab at Brown University were really important and helpful when we measured the ferrocrete samples. But happy to take questions.
Great. Thanks so much, Emily. We have time for questions. Go ahead, Shivangi.
Hey, hi. That is awesome. That's such a nice data set as well. I really like the suite of simulations you've been working with, and I wanted to take another look at that slide where you show the 9Ka versus 6Ka, the 4 plots with the divergence. Yeah, this one. A question. So these are anomalies at 9Ka relative to PI, I assume?
Yeah, each one is
but we've got the
6Ka or 9Ka minus the pre-industrial control.
Have you looked at something like this, but for precipitation? And the reason I'm asking this is because have you looked at the total amounts also for 9Ka and 6Ka? Like a similar plot, but for precipitation?
No, I haven't made like of the wind vectors and global precipitation. I was just focused on sort of total in the Western US for this project.
So because this makes me wonder if there were real differences in like, how big were the differences in precipitation between 9Ka and 6Ka first, like the difference between the two columns, but also if it's maybe the precipitation amounts are not terribly different, but it's just that the relative contribution of the two differs, the boundary conditions and the Green Sahara. Yeah,
Yeah, no, that would be really interesting to look at.
Because I feel like at 9K, it's perhaps just that the Green Sahara-ness of the Green Sahara was sort of saturated. And then it had more to do with the boundary conditions, but perhaps the boundary conditions, because they were less different at 6Ka, and hence the other factors swooped in, sort of like, this sort of a thing. Anyway, I'm going to write to you, and if you ever look into this, I'd be curious to know this.
Yeah, cool.
Awesome. I see the next on my screen is Daphne.
Hi, Daphne. Thank you. It was a great talk. I wanted to ask you if Delta 17 oxygen is not affected by the chemistry, NOx and sulfate and things like that.
Can you say the end of that again?
Is it not affected by chemistry? So chemical reactions in the atmosphere while it's transporting.
So we think evaporation along the storm track would affect CAP 17, but not very much. That's sort of the idea of the vapor transport model that I've been working on, is to see how much could CAP 17.0 be impacted along the way. I'm not sure if that's quite your question, but
No, I'm wondering about the atmospherical chemical reactions, like NOx in the atmosphere, changes in NOx, will that affect the signal in the isotopes?
yeah, I guess I don't know. Maybe we could try to include that as well in some sort of model, but I think the thinking is no, that it would not be affected by reactions with other gases. But yeah, I don't know if there's been much work on that.
There is some, but okay. Thank you.
Okay, we can have one last quick question from Allegra.
Oh, tried to show myself. Okay. Hi there. So maybe I missed it, but did you talk about the topography changes that you implemented at 9K? And also, I would say in general that your CAP 17, like it could be source changes. You could have anything that's relative humidity, like when the water's condensing, that could overprint on it. And if you're if your hypothesis is something relatively simple, rather than a really complicated model to track that down, you could do a super simple just painted water, paint the Atlantic blue, paint the Pacific red, see, does the purple change over time to evaluate that? It's a pretty easy experiment, I would think, to implement. But yeah, the 9K should be pretty significant topographic changes. The upper level velocities. I'm surprised that you don't see that.
Yeah, I don't. So my understanding of these simulations is that we're just changing like greenhouse gas concentration and solar insolation. I'm not sure how.
Oh, there was a big ice sheet, remnant ice sheet still at 9K. That's Laurentide, what doesn't completely disappear until closer to like 7 or 6, 7. But that I would expect to have pretty significant alterations on your circulation over North America.
Yeah, cool. Thank you.
Great. For the sake of time, let's move on. Our next talk is given by our Shrangi Dewari. Sorry, I probably mispronounced your name. Please take it away.
We can see her email.
You are muted.
Sorry, one moment. Okay. So I am Shivangi. I've just finished my PhD at the University of Quebec at Montreal, and I'd be very happy to get any feedback. Really, some of this work has been published, and some of it is still being written up. I realize I'm preaching to the choir here, but I'm going to talk about the remote impacts of the mid-Holocene Green Sahara on global climate. And everything I show here is the result of a multi-model comparison effort, which really could not have been possible without so many people. And I'm showing my PhD supervisors here, but of course also a big list of very helpful and very insightful collaborators. So this is from all of us. Okay, I'm going to bring you to present-day Northern Africa, large parts of which are occupied by the Sahara Desert, shown in white here, and bounded by the 100 millimeter isohyet. And during the mid-Holocene, you see the white is restricted to very few pockets. Now, what has happened is here are the different colors are showing us the different vegetational groups that occupy these broadly zonal patterns over Northern Africa following the isohyets. And during the mid-Holocene, these vegetational bands, they've sort of expanded northwards. And this is like a direct response to the northward migration of the isohyets once again. And it's just a generally much wetter and much greener landscape with a lot more surface drainage, including mega lakes. So this is what we call the Green Sahara, and generally we refer to it as the period between 11,000 to 5,000 years, although this does depend on the latitude, and also in some records, the onset is much earlier, but generally we're talking about the early and the middle Holocene. And there is just a wealth of proxy evidence for this period from multiple archives, multiple different proxies. So really, we've got a lot of confidence in the fact that there was a Green Sahara over Northern Africa during the mid-Holocene. And this region, the majority of the annual precipitation is brought by the West African monsoon, which is modulated by the seasonal migration of the intertropical convergence zone, which is further modulated by the insolation. So during the mid-Holocene, the boreal summer and fall insolation was greater over Northern Africa relative to the present day. And so we expect to see an intensification of the West African monsoon, which also makes sense given that that's the enhanced precipitation, which also enhances the paleovegetation distribution. Okay, so here is where we have the Green Sahara problem. Essentially that there is quite a substantial difference in estimates for the Green Saharan precipitation from the proxy reconstructions and from the models. And here I'm showing you the 6 Ka minus present mean annual precipitation changes. And the red box here is the Saharan zone. The box plot shows the estimates from the proxy reconstructions. These are pollen-based reconstructions. And then these circles here, the first group is the PMIP3 models, the second group is the PMIP4 models. So this has been a long-standing problem, and it's a widely recognized problem that if we, most models cannot simulate the mid-Holocene Green Sahara, at least in terms of the precipitation changes. And we think this has a bit more to do with how we generally simulate the mid-Holocene and perhaps less to do with the models themselves. This is a common, well, here I'm showing you the PMIP4 protocol, I would say the most widely used protocol for simulating the mid-Holocene, and the different forcings and boundary conditions which are suggested for the PI control and the mid-Holocene simulations. And we see that the protocol has these mid-Holocene appropriate orbital parameters and greenhouse gas concentrations, but vegetation and aerosols can be prescribed or kept interactive as in the PI control simulation. And just to point out that these are the protocols that I also use in the simulations that I will describe next. So this could potentially be the problem, and once again, it's a widely recognized thing. It was the sensitivity to prescribed vegetation experiments were part of the recommended experiments from the PMIP4 paper as well. So keeping all this in mind, we came up with this, we had this experimental setup where we are looking at outputs for the mid-Holocene and the pre-industrial from 5 different global climate models. I will point out that none of these have dynamic vegetation. We are dealing with prescribed vegetation in each case. And talking about the simulations, the 3 different simulations that I looked at, all 3 follow the PMIP recommendations for orbital parameters and greenhouse gas concentrations. But the third one, which is the MHGS simulation, the Green Saharan simulation, you could say, it additionally incorporates vegetation modifications. And then because this was not a coordinated Green Saharan experiment, the different models have different additional Green Saharan changes. So vegetation is common amongst all 5. It's not strictly the same, but it is all comparable amongst the 5 models and also comparable to the recommended sensitivity experiment by PMIP. But the dust, soil, and lake modifications, these vary between the different models. And just to give you an idea, here I show the vegetation changes in the ICSM simulation. These are not the same as the ones in the previous talk, though. Here, just to show the increase in the vegetation cover that is prescribed in ICSM. And then in ECR, there is an additional dust reduction prescribed. This was a reduction of 80% compared to the pre-industrial, and it was in accordance with the latest dust reconstructions at that time, which suggested an 80% decrease in dust. And in the University of Toronto version of CCSM4, the simulation also has the presence of 5 mega lakes in the mid-Holocene simulation, the Green Sahara simulation. So they're broadly the same, but not strictly. All right. So diving into the results, just a moment. Here, I want to show you the precipitation and the low-level winds for boreal summer. And these are the winds which are generally associated, the southwesterly winds associated with the monsoon circulation. I'm showing you the anomalies for the 5 different models from left to right, and these are mid-Holocene anomalies for the reference simulation relative to the PI. And as expected, there is an increase in precipitation over large parts of Northern Africa. It's up to perhaps like 0.3 to 0.5 millimeter per day. Not too large, I would say, but there is a greater increase in the core rainfall belt, slightly different in the 5 different models. But what is very consistent is that in each case, once we include the Green Sahara in our the prescribed vegetation and other conditions in our simulations, we see this substantial amplification of the orbital signal, with increases surpassing 5 millimeter per day during boreal summer, and also a further intensification of the southwesterly winds, bringing in moisture from the tropical Atlantic into the northern African landmass. So I would argue, well, this might be this is a no-brainer. It seems like there is an improved representation of the Green Sahara in the MHGS simulations. But really the key point I'm trying to make is that I think the MHGS simulations might also be a more realistic representation of global climate. And the one point I would really like to say is that during the mid-Holocene, what happened in the Green Sahara certainly did not stay in the Green Sahara. So here I'm showing, I'm just zooming out a bit. I'm showing mean annual precipitation and once again low-level winds. The 5th model was not a part of the paper at this point, so it's not included here, but qualitatively I've checked and it's all it agrees with the other 4 models. So the orbitally driven increase in precipitation over Northern Africa was also accompanied by a decrease over large parts of South America. And once again, as before, we see a sort of amplification of the same signal. In this case, it's a more widespread drying over South America. It's also not simply restricted to a weakening of the South American monsoon system during austral summer, but in fact, it's a more extensive, both spatially and temporally, it's a more extensive drying over the South American continent. We also compared well, I'm showing you the multi-model means here, and we compared our model signatures with the proxy estimates. This is a semi-quantitative metric that we use, the weighted coherence kappa score, but for all these 4 models, at least, the agreement between the proxy and the model improved upon the incorporation of the Green Sahara. And here's a list of the different proxy data sets we used. In nearly all the cases, you could also break this apart over South America or Northern Africa, and the improvement over the Cohen's-Kappa score is there in almost all the cases. All right. This is ongoing, but we think that the Green Sahara also led to increased temperatures over the Arctic. And just to note that none of our simulations have the high latitude vegetation changes. So again, we are focusing specifically on the Green Saharan impacts. So the first row here is the MH, the reference MH simulation, the anomalies in the mean annual temperatures. And you see there's a slightly greater warming shown in the MHGS simulations. And here I isolate just the difference between the two to see that there are fairly consistent signatures between all 5 models. I've also superimposed the TEMP12K data set and the estimations from the proxies included in that data set. And the Cohen's-Kappa score either remains the same or is improved in all the cases. It's improved, by the incorporation of the Green Sahara. However, we do feel that perhaps the models are warming the Arctic a bit too much because the root mean square error also increases upon the incorporation of the Green Sahara in 3 of the models. So that's something we're still looking at. Okay, but here I'm showing you some results for the equatorial Pacific. I'm showing you the 5 different models, but also then the estimates for the percentage reduction in SST variability over the boreal winter over the different Nino index regions. And the orange ones are for the reference MH simulation, and the green bars are for the Green Saharan simulations. And again, in nearly all the cases, the Green Saharan simulations show a greater reduction in SST variability, or as we interpreted this, the inclusion of the Green Sahara leads to greater reduction in the ENSO variability over the equatorial Pacific. We also saw a La Nina-like mean state. This was one of the other results. Here I'm showing the mid-Holocene Green Sahara anomalies for the boreal winter, and there's this greater La Nina-like mean state characterized by equatorial cooling as well as drying, and then a pretty clear southwestward shift of the South Pacific convergence zone, which is in the present day also, it seems to be associated with La Nina events. Just to isolate really draw attention to the effect of the Green Sahara alone, here I'm showing the MHGS anomalies, and these are relative to the reference MH simulation. And on the left, I'm showing you
3
the
minutes.
changes. Sorry?
3 minutes to
Okay.
the 7.
And on the left, I'm showing you the changes to the variability of the SSTs during the boreal winter. And there's this pretty consistent reduction in the ENSO variability as we across the different models. There's also quite a bit of drying and anomalous easterlies over the equatorial Pacific, driven solely by the Green Sahara in this plot. Okay. We think this is to do with the fact that the enhanced southwesterlies over the tropical Atlantic, which were bringing in more monsoonal precipitation to Northern Africa, also led to anomalous westerlies in the equatorial Atlantic and essentially inhibited upwelling and drove the Atlantic into a more Atlantic Nino-like mean state. So here it shows up, a previous study with EC Earth shows more clearer signatures in the MHGS simulation itself. But when we looked at the different models, we found a more consistent signature in the impact of the Green Sahara, slightly less clear and slightly less consistent in the MHGS simulations. The contours also show the temperature changes during the boreal spring, the February to April months, in fact, and North Tropical Atlantic warming during these months, as well as the Atlantic Nino events during boreal summer, are in the present day associated with more La Nina-like events in the equatorial Pacific. So that sort of gives us more confidence in this mechanism that we think was happening. Okay, so just to summarize, a lot of studies
I think now we have a lot of studies which have shown that the Green Sahara was not just a general phenomenon. So I've tried to summarize what I know so far, that the Green Sahara had these various impacts over the Northern Hemisphere monsoons, tropical cyclones, and so variability, and probably more. I do realize that most of the studies previously were based on a single model, and perhaps it would lead the community to have a bit more confidence in these results if we extend these results to multiple models. So I think really my key point is that I think if you are studying the Holocene climate over any region of the world, it really pays off to incorporate the Green Sahara, even if it's not, even if you think it might not directly be impacting your regional, the regional climate in your study area. So that is all. One of the studies has been published already, and again, I would love any feedback or questions.
Thanks so much, Wendy. Are there any questions from the audience? If you're in the room, I think John can monitor. I can't see whether you raise hand or not. I can start with a quick one. I find it's really fascinating that you have pretty big response when you have Green Sahara in the North Atlantic. You looked into what might be the cause?
I think it might be the what?
The cause for when you comparison between your Green Sahara and the no Green Sahara. I noticed a warming signal in the North Atlantic. I was wondering what could be the
Yes, I think it is an important response of including the Green Sahara, yes, but it doesn't explain everything because I'm sure the Atlantic Nini also played a pretty significant role in modulating the water circulation, and that bit is even the models which are not showing a very significant warming over the northern tropical Atlantic, they are still showing the other bit.
Right. Yeah, I just want to clarify. I was actually talking about the area close to the Arctic. So there's a warming signal. Yes, yeah, that one. So you can see like in 3 of the models that ICS and GIST and CM, you see this warming off the coast in the northern part of the North Atlantic or subarctic. I was just wondering, is there any explanation for this? Have you ever looked into it?
Well, currently, well, no, I don't have a straightforward answer to this. One of the other studies with ICSM, this was by Zhang et al. They did look into the impact of the Green Sahara, and they also see such a warming. But I think they explain it with an intensification of the AMOC. And this and their hypothesis is that because of the Green Sahara, a lot of moisture was sort of redistributed, and the Western North Atlantic was much drier. So there was an advection of these salty waters and sort of an intensification of the AMOC as a result. And so that could explain enhanced heat transport to the Arctic. This is one of the things that I'm looking into.
Oh, yeah, interesting result. Okay, last chance for questions from the audience. Sophia, go ahead.
I suppose I'll ask if you have any thoughts on the role of how we're prescribing vegetation in terms of the responses that we see in these different models. Do you feel that more of the uncertainty is just due to the different climate model simulations we're using, or is there a role of how we're prescribing vegetation for the Green Sahara and the remote impacts we'll see?
I think the first order important thing, the point to keep in mind is whether we are prescribing vegetation or not. And I say this because many of the responses that I tried to find in the Atlantic or in the Pacific were
impacted more by model biases rather than by the differences in the vegetation. I think at this stage, before, like, there are these two competing differences. So I say, I don't think that the vegetation differences in this study, for example, played the biggest role in the model responses.
Great. Thanks so much, Shivangi. For the sake of time, we have to move on. If you have more questions, feel free to type in the chat. And our presenters will check the chat throughout. All right, our last speaker is Alana Weiner. And please take away, Alana. I think you're one of the in-person participants.
Can you, yeah, we can see it.
Yeah, I can hear you, but it's not in full screen yet.
I can't unmute myself. Okay, unmute.
They can hear you.
Okay.
You want to mute your laptop?
Can you hear me? This because I'm in the room, so.
You want to mute your Mac, and it's from here.
Okay. So how do I view?
Yeah.
Okay. Oops. Got the wrong slide. Sorry about that. Okay. So I must say that this work was inspired by Shivangi's PhD thesis. I participated in a lot of the meetings. We discussed a lot about the Green Sahara influence on South American climate. And so, while we were discussing, I had this question of, would Green Sahara influence the ocean? And I'm interested in the South Atlantic. So I decided to take a look at the Green Sahara influence in the South Atlantic dynamics. And to do so, I decided to look at only one model, and that was, I elected the NASA-GISS model. And my slides aren't going. Oh, there we go. And, and one of the motivations that I think Shivangi shows that is like, okay, we see the Sahara is greening. And just last year, it was pretty amazing that we began to see unprecedented rainfall across the Sahara. And I'm showing you, the precipitation from NOAA and some vegetation anomalies also from satellite data showing that, you had increased rainfall and increased vegetation. So we're talking about, studying a probable scenario. So the more information that we can get about the physics and the dynamics, the more informed we are. So it's pretty clear that, the motivation came from Shivangi's work and on its influence extended to South America. So Green Sahara, like she showed in her last slide, is all over the place. And I'm particularly interested in these shifts in atmospheric circulation pattern, particularly the northward movement of the ITCZ, which I think has a strong correlation with increased North Atlantic Ocean temperatures. And also why the South Atlantic, just to remind you that the South Atlantic is really important to regulation of African and South America rainfall distribution. So it has a lot of control on variability in the rainfall, particularly the modes of variability in the Atlantic, and some contribution also to AMOC changes. And we can see that the South Atlantic does have a role for that. And, what are the research gaps and objectives of the study? We want to focus on continental impacts and the limited understanding of ocean-atmosphere interactions. So we can see the Green Sahara affects atmosphere circulation, but how does that affect, air-sea interactions? So the key questions are, do we see this influence on the South Atlantic? And also, I'm going to focus a lot on African megalakes impact on the circulation. And of course, we're going to see that from an ocean response perspective. And just, bringing back the megalakes, I was absolutely fascinated that during the Green Sahara period, Lake Chad expanded to over 400,000 kilometers. And we see a reconstruction of what it kind of looked like. And I don't know if you can see it. And this is the current Lake Chad. So it was really expanded and representing a dramatic change from present day conditions. So it's kind of cool that we had a model experiment that incorporated specifically, these mega lakes. So talking about models, I'm going to use the GIST E21 2.1G model. These are the specifications, and I look at 4 different experiments: a pre-industrial control, mid-Holocene reference, the PMEP, 4 protocols, one with prescribed vegetation, which is our GS, and one with these mega lakes, which is going to be really interesting to see how they compare to each other. And this is basically what I'm showing, just how all these experiments impact the South Atlantic. So let's start with sea surface temperature changes. And the way these panels goes is that, upper left is always the PI control. So we have an idea what, pre-industrial distribution of the variable looks like. And then next to it, we see the difference relative to the reference, the PMEP for protocol controls and temperature. And then we see the pre-industrial relative to the Green Sahara experiment, and the pre-industrial relative to the lakes. And just, for curiosity, in the bottom, we can see the differences between all the mid-Holocene experiments, the GS to 6K, which is the reference, and the lakes to GS. And what are the key findings here? We see, people showed before, the general cooling trend compared to PI, but we see a warm anomaly near 30 South. The lake simulations show a most extensive warming, and that's a panel D in your right-hand side, on my right-hand side, and temperature differences up to 0.3 degrees C. And where you have the stippling, it's where the results are not significant at 95%. Now, we're not really used to look at, vertical distributions. Look on the subsurface ocean, and this was really quite fascinating for me because we saw the cooling in the upper tropical South Atlantic. We see a warming in south of about 50 South, and the lake simulation patterns show that upper 200 meters is cooling and a surface cooling at about 45 South. And we can see that the difference are pretty remarkable when you think about that we're looking until 1,400 meters below the surface. So we can see that the Green Sahara and the lakes can have an impact on the subsurface ocean. And then if we want to look at the subsurface ocean or deeper in the ocean, we want to look at water mass properties. And of course, salinity is part temperature and salinity together do characterize these water masses. And here I can show you, and I was really surprised to see how, you had these impacts on the vertical profile of salinity. So we basically a freshening of the South Atlantic central water, which is more towards the north of the domain. We see modified Atlantic intermediate water extent, which the key drivers would be the enhanced freshwater input, where we have more precipitation, so you get more freshwater input, altered evaporation rates, and changes in water mass formation. So you're changing temperature and salinity characteristics, so you're changing how these water mass form. Also, if we look at the atmospheric circulation that would impact on, all the drivers that I just mentioned, I don't know if you can see very well. So, the red panels are sea level pressure changes, and the right panels are the wind patterns. And so we have the wind vectors that are plotted are only the ones that are significant. And, summarizing what are these changes, we see, big changes in sea level pressure patterns which induce the wind changes. So the wind patterns change in response to the changes in the tropical high, for example, it shifts, and this also induces winds changes in the trade winds. And if we look at zonal wind changes, which are basically what's driving, mixing in the oceans, and this is pretty cool. So we see the zonal average winds on this on the left-hand side panel and the differences in the right-hand side panels. And we can see that westerlies intensify, particularly, in the south of the domain between 30 and 55 south. We see that the westerly winds the strongest in the GS simulation. So, which is a response of the shift in the sea level pressure and in intensity. And the lake scenario shows also a relative weakening of the westerlies, but it's most pronounced north of 55 south, where we see that red pink curve in the right domain panel, which is the lakes. And finally, this plotted is the barotropic string function, which is a measure of the circulation, of the gyro circulation. And so you can understand what the changes are. I have in all plots the PI control, the white contour, which is the zero contour, which indicates the changes between the cyclonic and the anticyclonic circulation, the subtropical gyre and the polar gyre differences. And when we look at the difference between the panels, we see that we have significant subtropical gyre changes. We have the subpolar gyre weakening, and we can see that in the lakes minus PI, we see that we have an enhanced circulation, gyre circulation, which means that GS also induces a stronger circulation in the gyre. And this implies a lot of complex feedbacks that I didn't analyze all of them. So this is a short talk because the major discussion and conclusions I try to summarize. What are the implications of such a study? Well, I'm showing terrestrial oceanic coupling, which for me, I think this is pretty interesting because not many people show that land changes will have an impact in ocean circulation. And furthermore, it could have an impact in water mass modification. Well, keep in mind, this is a very idealized study, but it's an indication that these changes that happen, in the mid-Holocene could have impact ocean circulation, below the surface as well. It's also a study that shows systems interaction. So we have vegetation and megalakes affecting ocean, so we have a warming effect and we have a freshening effect as well. And we see modify atmospheric processes that will impact on the ocean circulation patterns. So, and then the key takeaways are the Green Sahara impacts the South Atlantic Ocean. This is pretty new, below the surface, and we have enhanced warming with the megalakes and modified water mass characteristics. And what will be the possible climate modeling implications? So again, the importance of these vegetation effects and the terrestrial oceanic coupling, and also the role of lake feedbacks. And I thought that was pretty interesting too. So yeah, it's a short talk. Thank you.
Thanks so much, Alana, for this inspiring talk.
Heidi has a question.
Yeah, go ahead.
So I don't know the GISS model, but I know in other studies, dust, when you have a green Sahara, the reduced dust is some of the responses. In the GISS simulations you showed is either when they green the Sahara, is there reduced dust, or do they reduce dust, prescribed dust?
I think the dust is prescribed.
Okay, and it's reduced.
Yeah.
Okay, good.
Great. We have time for more questions. I actually have a quick one. Out of curiosity, how is the river routing being done in the GIST model? And I was curious because you mentioned that the lakes have pretty big impact. I was wondering, when you build lake chat in the GIST model, where would the water drain into, and is it affecting the ocean water mass?
I have to say, I don't know.
You want me to answer that one?
Oh, please, Allegra. I was going to call on you, but thank you. Yeah.
Sure. So
Let me.
So the GIST model, every surface grid box is prescribed a cardinal direction. Like we literally number every land box from 1 to 8, and that is the direction that water flows. And lakes are variable. So lakes are allowed to, there's an initial condition that has to do with how deep the water is and what the initial fraction of lake is, but then lakes are allowed to grow and shrink within their grid box, and they're allowed to spread into adjacent grid boxes following the whatever is downstream. So you can absolutely have big changes into what's being fed into the ocean based on what's going on the land surface. Yeah. This particular one is the river routing is identical to the pre-industrial, but for like deeper paleoclimates, literally somebody gives me a river catchment basin map, and I by hand go in and do things, and it is the most intensive part of the paleo simulation. Yeah.
Yeah, it sounds similar to the CSM, except the lake area in CS cannot be changed. But it'll be interesting to see if there are any geological evidence to know where the lake chat might flow towards.
Yeah, I haven't gone back in and directly constrained the size, like the size that the lakes evolved into. Because the lakes are allowed to evolve, it's yeah.
And in you guys' simulation, it
for
does
super long, and then the lakes would be like whatever equilibrium with the freshwater balance of the entire simulation, but we kind of wanted it to be closer to the prescribed value. So these runs were only done a couple hundred years extra, so that prescription was still like a big part of simulation. Yeah.
Thank you. I think John, and followed by Betty. I think
Yeah,
for everybody else, I think we're running out of time, so you have to go. If you want to go grab lunch, feel free to go. I think John and I decided we want to stay on schedule, so please come back at 1 o'clock Mountain Time for the next session. For the next session. But for everybody, if you're not in hurry to get lunch and if you're interested in discussion, please stay on.
Yeah, my question is about the ocean response, for example, SST and potentially current response. Do we have proxy data to validate that?
Yeah, actually, there's some that I know of, but very near the coast of South America. So not a basin-wide proxy.
Cool.
Yeah. So we did a reconstruction of a compilation of all mid-Holocene proxies for South America and the coast.
Yeah, some proxy you can potentially use to back out the geostrophic flow. So potentially you can also evaluate the ocean current change.
Yeah, that's a good idea. Actually, I lowered my hand. I think Allegra kind of answered it on what the lakes could do in terms of getting bigger or getting smaller, depending on how much precip you actually give them. I know. It's quite amazing, right? That it has
So the reason I can tell you a bit more about that. The reason we did that is that, everybody has boils and warts, so do we. And the precipitation biases, if you have a positive precipitation bias, and you don't allow your lakes to expand into the surrounding grid cells, you can never get enough evaporation to catch up and balance you out, and you can end up having long-term drifts in like the mean salinity of your ocean. So the decision was made, it gets quite like about 15 years ago, to allow lakes to expand beyond one grid box, to grow to be like the size that they were sustainable, basically, to take care of that salinity drift problem.
Yeah, the opposite, Allegra, is if you don't have enough precipitation, they're going to shrink and shrink and shrink, and which could happen in, not the simulations, just with orbital forcing, I would think.
Absolutely. Absolutely. Yeah.
Awesome. That concludes the section. And thanks for all the speakers and participants. And we'll see you guys at 1 o'clock tomorrow.
Perfect, thanks. Yes, so let's get started with our next session. It's gonna, be the same procedure as the previous two. So I'll give you, I think, a 2-minute warning before the 17 minutes allocated for your talk, so we can leave some time for questions. Great. So our first talk is by Ron Fung. We're going to hear about Pliocene climate in ICESM1. Take it away.
Thanks for the introduction, Sam. And hi, everybody. Good afternoon. I think I would like to use this opportunity to talk a little bit about the ongoing Climate 3 effort in collaboration with the Paleoclimate Working Group, John, Betty, Anta, and potentially Sophia group. So to start, I would like to update a little bit on what happened to Climate 2 since the publication of the large-scale paper and the initial wave of papers. So for the Pliocene modeling incorporation project to the large-scale paper, we contributed the CSM4, CSM 1.2, and CSM2 experiments with the full mid-Paleocene or mid-Pliocene boundary conditions. But since then, we carried out quite a few sensitivity experiments with CSM2. In one of them, we kept all the mid-Paleocene boundary conditions, but run the case with 280 ppm CO2. And in addition to the existing PI control, we also run 2 CO2 sensitivity experiments with 400 ppm and 560 ppm CO2 with pre-industrial boundary conditions. And we also carried out round 2 sensitivity runs with just the Lancy mass and symmetry changes of the Pliocene, and with 400 and 280 ppm CO2 separately. So all those experiments are published in the paper that are published in 2022, and the data are all completely available. Feel free to contact me if you are interested in exploring those simulations. So far, we looked at large-scale hydrological cycle, looked at Southwest US hydrological cycle, and looked at the pattern effect. But if you have other ideas, feel free to reach out. And I'm also interested in exploring other ways to distribute the link. I know that we're busy and writing email takes time. So yeah, if John, you guys have a place on the Paleoclimate Working Group webpage, I'm also happy to post a link there. So for Climate 3, this is upcoming Pliocene modeling comparison phase 3. There are some changes, but also some consistencies with Climate 2. So for Climate 3, we'll return the mid-Paleocene boundary conditions for the core experiment. So you can see for the core experiment, this lake Pliocene, which is equivalent to exactly the same as the mid-Paleocene experiment in the Climate 2, but there'll be new models participating, obviously. And there's also a new target of the early Pliocene here. So for this early Pliocene, the experiment will target 4.474 or 4.870 millions of years orbit. So the reason for selecting those 2 time slices is because they have consistent orbital forcing distribution with pre-industrial. It's very close. will also be new sensitivity experiments in this little chart here. This is in the Haywood 2024 paper, which laid out the climate theory protocols. There'll be optional sensitivity experiments. You can see the CO2 sensitivity experiments with pre-industrial level and 2-time pre-industrial level planned for both the late placing boundary conditions and the pre-industrial boundary conditions. And another late placing with the early placing CO2 level experiment and sensitivity experiment testing for the changes of the East Antarctic ice sheet that implemented in the late placing boundary conditions, and their sensitivity experiments with the extreme hemispherical distributions of orbital forcing, which can be used to conduct data model comparison in terms of finding out the uncertainties induced by the orbital variabilities that are not captured potentially in a lot of proxy records that does not resolve orbit. And there are also dynamic vegetation sensitivity experiments. So here's a table of ongoing and planned experiments at my group. So we're hoping to run this list of CO2 sensitivity, the list of climate 3 experiments using 3 versions of models, ICCS 1.3. So this is the version that tuned by John and then used in our paleo weather experiment project that was led by Betty. CESM2, this is a model that we use to run the late placing or mid-fraction experiment for climate 2, and we already have quite a few sensitivity experiments for it. And CSM3, I would like to hear about the development at today's discussion. I think I started poking around it, I have not gone much further than that. But I think this year would be the year that I can focus effort into developing those simulations. So currently we're running the late placing, early placing, the late placing at 280 ppm CO2 and late placing 180 ppm CO2 with ICS 1.3. And we have pre-industrial 400 ppm, pre-industrial 490 ppm. This can run at any time, but ideally, I would also like a late placing at 560 ppm, but I would like to reach out to people. Maybe there is already ongoing run, so that I don't have necessarily have to run. And after I run the early placing a little bit better, a little bit longer, the plan is to branch it to run early placing 280 ppm CO2. And my students are working on creating boundary conditions for the late placing with present day or pre-industrial East Antarctic ice sheet and the late placing with no change to the land sea. And for CSM2, we already have obviously pre-industrial and late placing, and the early placing, which uses very similar symmetry to our ICS 1.3 versions of models, so that's about to run. And we already have the pre-industrial 400 ppm CO2, late placing 280 ppm CO2, and the rest of CO2 sensitivity because we already have the boundary conditions are ready to run. And for CESM3, obviously I have none of those, so that still need to be developed. And for the rest of this talk, it's going to be pretty short because I don't have a lot to show yet. I'm going to focus on those 3 experiments, the pre-industrial with ICCS 1.3 and the late and early placing with ICS 1.3. I'd like to give you a very quick overview of climate evolution from early to late placing. So this figure here on top shows the benthic oxygenating of reconstruction and compiled across all ocean basins. And you probably have seen this a lot of times, but ignore the yellow shading here. That's not the interest. But look at before that. So the early Pliocene, roughly from 5.3 all the way to the late Pliocene, which is our mid-Triassian experiment, 3.0 to 3.3 million years. You're actually roughly looking at this part of the curve here. So you do see there's enrichment trend of the benthic O18, which could reflect deep ocean cooling or some kind of expansion of the ice sheet. And there are quite a few studies, especially using the Andrew core in Antarctic. They did find warmer Western Antarctic region. And sedimentary records, their sedimentary records do suggest the sea level stand would be higher during the early Pliocene compared to the late Pliocene. And here's a compilation CO2 record. This is a little older, but in general, there's quite a bit of uncertainty to start, but in general, a lot of records do seem to show a general declining trend of CO2 levels from the early towards late Pliocene. Also took the data from the Herbert 2016 compilation to see how much, to see the structure and potentially how much the ocean has cooled. The caveat is I've only taken the arithmetic average across the sites for different latitude beings. I have not taken into account, let's see, latitude, area weight, things like that. So the actual value could be a little bit different if we're taking into account like area weight. But just to first look at those records, the top panel shows absolute reconstructed temperature, and the bottom one shows the temperature change relative to the pre-industrial. Just take a first look at those records. Ignore this gray bar because this paper is about late Miocene cooling, but from the late after the late Miocene cooling, starting from the Pliocene, which is 5.3, around 5.3 million years, you can see like for most of the records, you can see a cooling trend from the early to the late Miocene, right? And I calculated the amount of warming relative to pre-industrial separately for the late, the early Pliocene. The late Pliocene, we're using this time slab of 3.0 to 3.3 millions of years ago. And it's about 1.4 degrees in the tropics and about 3 degrees in the northern southern mid-latitude. And the warming is symmetric. For the early Pliocene, it's about 5.5 degrees in the northern mid-latitude. But it's only 4.5 in the southern hemisphere. And it's about 2 degrees in the tropics. So at least if we just take arithmetic average of sites from this data set, the early Pliocene actually has a little bit of more, amplified northern hemispherical warming compared to southern. And at any latitude band, they're definitely warmer than the late Pliocene. The key differences in prescribed boundary conditions. I know this is very controversial, but this is a choice of 5 and 3. So for CO2, for late Pliocene, we're using 400 ppm for the experiment. And for early Pliocene, we're using 480 ppm, which is to consider that the trend in the CO2 reconstruction is not great. There's no very clear evidence about how high early Pliocene CO2 should be, and based on the general declining trend, the experiment protocol decided like by 480 ppm. It's probably a good guess. For the paleogeography, the early Pliocene boundary condition used in the model actually featured open Central American seaway. This is very controversial because their geological evidence suggests that Central American seaway could have closed during the Miocene, even as early as 12 to 15 millions of years ago. But there are also paleoceanography evidence looking at potential salinity changes across the Central American seaway. Those turn to put the closure time of Central American seaway towards the early Pliocene. And here just shows a Central American seaweed configuration proposed in the experimental protocol. And this is what implemented in the ICS 1.3. And I'm going to show the results, simulated early placing versus late placing. 3. And the transient evolution of the simulation is actually really interesting in the early placing. But we'll start with the late placing. So both early and late placing simulations are initialized from the CS 1.2 late placing simulation that we published. And you can see this blue curve here shows top of atmosphere energy imbalance. This is in the late placing simulation. And the red ones shows the global mean surface temperature. You can see for the late placing simulations, the simulation, there is an initial warming trend, which is accompanied by the decrease in the rest dome. The simulation visually roughly reached equilibrium around 500 model years onward. From 500 model years onward, don't see much of a trend anymore. At the end of the year 900, so I take the last 100 years of rest dome, it's about 0.1 watts per meter square, and the global mean surface temperature is 18.2 degrees, which is very similar to our CS 1.2 late placing simulation. And I also plotted the ice fraction, which I think we unfortunately initialized with a cold model year. So actually initially we had a high ice fraction, but eventually it stabilizes together with the rest of them. However, if you look at early placing simulation, the transient
2 minutes.
Okay, great. The transient evolution goes pretty crazy. The chart here shows the rest dome in blue, and the red is the temperature evolution. So you can see the global mean temperature cooled rapidly initially and then warmed up. And then there's almost some sort of instability going on in the simulations, and the temperature cooled drastically around year a little bit over 340-ish. And then the temperature stayed low. What happened in the simulation is the AMOC quickly crashed when I opened the Central American Seaway in the simulation and stayed pretty much crashed. And there is a little bit sea ice instability going on between 300 and 350 years. We see a rapid growth of the sea ice in the simulation. And this not exactly, but this actually matches the bipolar seesaw type of climate response we see when you have collapsed AMOC. So this is Northern Hemisphere time series, and this is Southern Hemisphere time series. And you see that with AMOC collapse, you see a rapid increase in the sea ice fraction in red. This is actually reference to the right. And you see a rapid cooling in the North Hemisphere surface temperature. And again, you see this very interesting instability developed in the simulation that the sea ice massively expanded between around year 330 or so. And then that corresponds to a rapid cooling in the hemisphere. And even Southern Hemisphere felt a little bit about this cooling, but it did not penetrate to the high latitude of Southern Hemisphere. You see in the Southern Hemisphere, you see the contrast, you see the rapid warming and a rapid sea ice decline with AMOC collapse. And you see this little bit cooling, which potentially penetrated from the north. And this is just another figure, shows the profile of the the meridian overturning function in the Atlantic. In the late placing simulations, we get consistent results with what we published in 2017, that the gateway changes induces a stronger AMOC. And this main mark, which is shown in some other studies, is shallower than the pre-industrial, potentially due to the effect of CO2. And in our early Pliocene simulations, we no longer have AMOC. What we have is very similar to what we have in Pacific today, is the tropical subtropical overturning shallow overturning cell. We can see that in the changes to the ocean mixed layer depth, that we no longer have deep water formation in the early Pliocene experiment. And we have, but interestingly, we have some other development of mixed layer, deepening of mixed layer. Off the coast of North America, off the coast of Asia, it's actually in the Kuroshio extension region here, and also off the coast of the South America. And here's another map. So in general, of the sea surface temperature shows you this bipolar seesaw. This is taken the average of lots of years model simulation. There's still got the early Pliocene simulation still ongoing. So this might change a little as the simulation goes. But for now, there's more warming in the southern hemisphere compared to northern hemisphere in the early Pliocene relative to pre-industrial. And in the late Pliocene, the warming in the simulations is hemispherically symmetric. And in the early Pliocene, which could be consistent with the proxy reconstruction, is that Antarctic is really warm, and it's much warmer than the late Pliocene. The Southern Ocean is also substantially warmer in the early Pliocene, late Pliocene. So what we learned so far from the experiments, opening cast collapsed AMOC, which is probably not surprising because other experiments also find similar results, which led to the bipolar seesaw response. But interestingly, in the ICSM 1.3, that we see this Arctic sea ice going. And I'm curious to hear if other people, maybe other model, I don't know if Allegra knows the early Pliocene simulation. Curious to hear if other models have this phenomena. And well, as I mentioned before, the asymmetry of warming in the early Pliocene experiment still needs support from proxy SST reconstruction. Based on the simple arithmetic average, it's not consistent. However, the enhanced warming around the Arctic and potentially high sea level stand could be consistent with the proxy record. And there are hints of development of ocean convection at new locations in the early Pliocene simulations, which I cannot tell for sure yet. This run probably needs to run for a few millennia to be able to tell if ocean circulation develops. That's all I have. Thank you.
Great, yeah, thanks, Ron. We have time for maybe one quick question. Any questions? I can't tell if anyone in the room is raising their hand. No?
Maybe I can ask a quick question about the AMOC. I haven't followed the literature on this. So even if you run very long simulation, the AMOC will still be collapsed with the Central American seaway closed?
I think some of the simpler models do turn to show that, but it is model dependent.
Okay.
So that's why I'm not entirely sure if this result might not change as I run the simulation for longer. But so far, it looks like it's not on the trend of rebounding. It's more on the trend of stabilizing. And instead, I started to, in the simulations, like I showed in mixed layer depth, I started to develop some of the other ocean convection sites.
Thanks. Yeah, I guess we'll move on to the next talk then. Feng Zhu, you're in the room, right?
Yeah.
Yeah, great. So the talk will be about bridging the Miocene climatic optimum warmth gap with equilibrated isotope-enabled CESM simulations.
All right, thanks. Hello everyone, my name is Feng Zhu. I'm a paleoclimate software engineer and data scientist at NCAR. So I modified my title a little bit to make it more formal. addressing the middle mouse in climate optimum worms conundrum with equilibrated isotope-enabled CSM simulations. We'll be talking about what the MCO worms conundrum is and how we address this conundrum with equilibrated isotope-enabled CSM simulations, as well as some implications. So MCO provides invaluable insights on warm climate and is therefore a good analog for future climate change. So in this science paper, Westhold et al. 2020, they suggested that the global mean surface temperature during MCO is equivalently between two warming passes, the RCP 4.5 and RCP 8.5. However, the exact value of GMST is still under hot debate. And our study here aims to answer this very fundamental question: how warm was MCO? So previous attempts have been made to estimate the global mean surface temperature of MCO based on surface temperature proxy records. For example, in this study, the MILMIP-1 study by Bors et al., they reconstructed the MCO GMST to be around 5 to 10 degrees C warmer than the pre-industrial, based on a very simple linear regression model fitting zonal mean temperature profile against the surface temperature records. So this method has a major limitation that it ignores the spatial heterogeneity of the surface temperature, given that we only have a very limited amount of the records. To overcome that limitation, an optimal alternative approach is to infer the GMST based on deep ocean process. For example, in this study, Hansen et al. 13, they took a two-step approach. First, they reconstructed the bottom water temperature based on the benthic forum delta records, and then translated this bottom water temperature to global mean surface temperature. However, they suggest that the GMT should be around 4 to 5 degrees C, leading to a significant gap between these two reconstructions. But these two steps are subject to potentially large uncertainty and biases. So in the first step, it requires a good quantification of the impact of global ice volume and seawater chemistry on the benthic forum delta records. And in the second step, it relies on an assumption between the surface and deep ocean temperature. So even if we bypass the second step and focus only on the bottom water temperature, we are still limited by the first step, these two factors, and we still get a significant gap in this bottom water temperature when we compare different processes. So it seems that processes show a significant MCO worms gap, which we refer to this worms conundrum. Then can model data comparison be helpful on this topic? Well, it seems it doesn't help much if we still do the model data comparison in the GMST temperature space. For example, here we have a couple of MILMIP-1 simulations, and if we compare simulations with low CO2 configuration, we have a better agreement with H13, the zeta-18 based reconstruction. And if we use simulations with a high CO2 configuration, we have a better agreement with the D21 reconstruction. So it's inconclusive which case is more likely. So here in our study, our strategy is to, instead of do the comparison in the temperature space, we do it in the process space. So here we leverage still the benthic forum delta T, which is one of the most reliable proxies to reconstruct past climates because they are well preserved in a stable environment and they are representative of the global mean. And we do a comparison in the proxy space, also known as the forward modeling, to better handle the nonlinearity and the multi-environmental variables in the relationship between temperature and the benthic delta 18. But this approach requires our simulations to be first equilibrated, to have the equilibrated devotion, and second to be isotope enabled. However, isotope enabled simulations featuring equilibrated devotions are rare. So for example, in Maomip-1 simulations, most of them, they are not isotope enabled and they are relatively short, up to 2000 years in length. So our study here is unique and in offering this missing piece. So we leverage the state-of-the-art isotope-enabled CS 1.3 high-res. So ICSM is one of the best models simulating the present-day observations, as well as the past extremes, cold and warm conditions. And we use the same setup as in the Maomip-1 simulations, but we developed two simulations. One is warmer, another is colder. So here we see our two simulations gets equilibrated after about 5,000 years. So this is the global volume mean of the ocean. And then again, if we compare our simulations and the proxy reconstructions in the temperature space, we are still inconclusive about which case is more likely. So now let's move on to the proxy space. So here we selected 5 benthic forum sites, sampling different regions of the globe. So their average can be regarded as a good example, good sample of the mean of the globe. And we get this on this range for the benthic forum delta T observations. And then we translate our simulated model variables, the ocean temperature and the seawater delta T in the model, into the proxy space, the benthic delta 18. And also we consider the impact of the ice volume as well as the ocean chemistry based on pH. We constructed this so-called process model based on the calibration model in this paper, as well as the estimate of the distribution of the MCO background seawater delta T and the ocean pH values based on these studies. So the first part in black is deterministic, and the second part in blue is probabilistic. Therefore, our prediction from the model of the benthic delta T, here we have the gradient blue indicating different probabilities. And then we can do a cumulative, we calculate the cumulative probability distribution bounded by the uncertainty of the proxy observations. And we can then do a kernel density estimation to indicate the probability of different CO2 cases. So here we see our, it gives the distribution of the likelihood, and this likelihood could be remapped to the temperature space. So in the bottom temperature space, here we get the maximum likelihood to be around 6 degrees C, warmer than pre-industrial, with 1 sigma standard deviation around 1 degree C. And also remember to the global mean surface temperature, our maximum likelihood estimate is around 8 degrees C, with plus minus 1 degree C. So that's basically our answer to that fundamental question, how warm was MCO? And in addition, we have several interesting findings. So the first is that we find that the deep ocean equilibrium is also important for the surface. Here we are comparing our final state in our 3 times CO2 simulation, comparing against the early stage after 500 years. So we see the high latitude Southern Ocean shows a very significant warming effect up to 5 degrees C. And we find that this is related to the region of the deep water formation. So basically, we find that this high latitude Southern Ocean shared a very similar density to the deep ocean. Therefore, they are basically the same water mass, and they share a similar time scale for the ocean mixing. And we know the deep ocean takes a long time to mix, to stabilize, and therefore this surface also takes a long time to get to its final state. Therefore, there's a big difference between the final state and the early state. The second point is that our reconstruction, our estimate, most likelihood estimate, is in a very good agreement with the independent SSC records. Here we are comparing to the records in the Miami Point paper, as well as the latest paper by Nirenberg and Herbert in the North Pacific. The only obvious difference is in the North Atlantic. And this is a well-known discrepancy. However, the cause is still an open question. And one hypothesis in a recent paper by Xiaoqing Liu et al. Is that it's related to the strength of AMOC. So in our simulation, we don't have AMOC, but if we, in their experiment, if we open this Canadian Arctic seaway, then it will trigger a vigorous AMOC, and it will increase the northward heat transport, leading to these very warm observations. So it's still a hypothesis, but overall this is an open question and requires more investigations. Yeah. So another point is that we find a very beautiful one-to-one surface deep ocean relationship during warm climates. It works for the global mean surface temperature as well as the global mean sea surface temperature. This slope is very close to 1. And so here we confirm and highlight the hypothesis in H13 and the Evans et al. 2024. Okay, now given that our estimates and H13 are both based on Deloitte benthic, and actually H13 is based on one of the sites we used, you may wonder how exactly our estimate is so different than H13. So here we do some attribution analysis. So if we look at the detailed equation H13 used and compare to our process model, we see that they are essentially in a similar structure. So if we ignore this second term, this non-linear term, and compare the other terms, we find that we have different slopes, we have different intercepts, and we can also consider the impact of the ice volume and the pH values. So the very first obvious difference in our modeling is the pH correction. And if we do not conduct this correction, we will get our estimate to be 0.7 degree colder. And that explains about 40% of the original difference between our estimate and the H13 estimate.
2 minutes.
Okay. The second point is actually a very simple reason, the spatial representative. So H13 used only one site with this measurement value, and our estimate is based on the average of the 5 sites. So it's a slight difference. And that accounts for about 30% of the difference. And lastly is ice volume. So here basically, since we have a different slope, we have different intercept, to make it consistent with H13, we have to move our curve downward. So we, instead of using this distribution around the negative 0.4, we use another value around the negative 0.5, then we will get an estimate very close to H13. So that explains the around 30%. So that here we see the importance of different factors. Okay, so basically that's it. Ultimately, our study shows the first long run ICS simulation for MCO featuring 4 equilibrium in deep ocean, and we developed a novel analytical probabilistic approach to infer the GMST and the bottom water temperature. And our estimate is warmer than what's mentioned in the science paper, but it's in a good agreement with independent process. And we confirm a one-to-one surface temperature, surface deep ocean relationship. That means when we don't have enough records in the surface, we may turn to the deep ocean to perform some analysis. And lastly, our estimation suggests equivalent pathway of RCP 8.5. That means if we end up with this warming path by 2100, we will physically revisit MCO. So that means highly reduced Antarctic ice sheet, higher sea level, global ecosystem, hydroclimate changes. That's scary. So that's what I have. Thank you for your attention.
Great. I have some time for questions. Anyone?
We have one question in the room. Go ahead.
Yeah, thanks, Feng. Really neat stuff. I have a question about the one-to-one relationship. Wondering if you could say what you think might be causing that. I think we think of there being a relationship between the deep water mass properties and the places and times in the surface ocean where deep water is formed. So is this a relationship between the global sea surface temperature in deep water, or is this telling you something about formation mechanisms?
Yeah, so physically, I think it's related to this linkage between the highlights to the Southern Ocean and the deep ocean. And here we are comparing the global mean, and that's kind of a statistical result. So basically, we have the linkage between the deep ocean and the highlight surface, and this highlight surface and the global mean has this statistical linkage. So we know there's a polar amplification effect. So and that will counterbalance between this high latitude warming. So eventually, statistically, we get this relationship, and we find that this is only works for climate. So if we have ice sheet for this high latitude, then that will actually disrupt this relationship. So there's some physical mechanism, but it's also a statistical result. I hope that answers your question.
Other questions? Well, yeah, thanks, Hong. Yeah, so Ron, do you have a question?
Oh yeah, just curious. Then when you look at just the CO2 sensitivity experiment with pre-industrial, for example, have you ever looked at CO2 sensitivity experiment just with pre-industrial boundary conditions? And do you still get this one-to-one relationship? That would be curious.
So we have tuned our pre-industrial simulations. It's balanced, and we find that it's about 1 degree warmer than some of the other pre-industrial simulations. But here, since we are looking at the delta, so it's the warming part compared to pre-industrial. So our conclusion should be independent of the absolute values. Does that answer your question?
I was curious whether this one-to-one relationship is dependent on the paleogeography and the fact that you potentially don't have AMOC because of paleogeography or not.
Yeah, so we actually cannot tell based on our simulations because we haven't tested other geography setup. But based on this events et al. 2024, they look at the different simulations for other time periods in warm climate. So in their study, they also show a very robust one-to-one relationship. But again, I think the more important factor is the ice sheet. So if it's a colder climate, then we don't have this relationship.
Okay. Yeah, we're a little behind. So Sophia, would you mind putting your question in the chat? Great, thanks. Yeah, our last talk for this session is Dan Amrine. We'll be talking about online data assimilation for deep time paleoclimate.
Awesome, thanks, Sam. I'm gonna come up here. Is that okay? Because I love attention. Okay. Great, thanks so much for being here. I'm excited to share this work with you today. I'll start off by acknowledging that this is a collaborative project. So most of what I'll show today are thoughts from me and Feng and results from Feng, with a lot of contributions from folks at University of Arizona, UC Irvine, other folks here at NCAR, and University of Oregon. And this is funded by Heising-Simons. So what we're interested in is online data simulation for deep time paleoclimate. How do you combine constraints from models and data to get the best possible picture of how the Earth looked a really long time ago? Zero order, how do you advance? There you go. Okay, and so I'll spend a little bit of time just outlining the project, what we're trying to do. No? My screen sharing is paused. Okay, can I advance that? Let's see. Are we going to have to do it this primitive way? Okay, sorry, we'll do it this way. I'll first talk a little bit about data assimilation and what it is and what we're not doing. I'll talk about some things that we've tried so far and something that we're excited about. And then I would love to hear from people what other kinds of things we should be doing at this point, or what kinds of things we might be missing. Okay, so this paleo weather project was inspired by these questions. So as we look back millions of years in time at warm climates, how do we expect weather and weather extremes to behave? And not just like to what extent do we see changes in things like tropical cyclones and atmospheric rivers in other climates, but also to what extent do they contribute to maintaining those warm climates? And then relatedly, when we're thinking about weather and weather extremes, what is the geography of habitability on the Earth at this time, right? Where could flora and fauna actually live, and to what extent did climate control that? So the scope of the project is ambitious. It looks at 4 time periods over the last 100 million years, the Cretaceous, Eocene, Miocene, and Pliocene. And the workflow is to begin with some low resolution simulations, some ensembles of simulations that try to probe the space of all of the uncertain model and boundary condition parameters that we have. And then to bring in data constraints through data assimilation, focusing on proxies of sea surface temperature, which are among the most robust proxies that we have for these time periods. And then to use these data constrained solutions to drive high resolution paleo weather simulations. So in terms of the data assimilation challenge for this problem, we would like to perform data assimilation on these long time average paleo proxies to generate an online CESM simulation that fits the data within their uncertainties. And then we're going to use this online solution in a different CESM configuration to drive a weather model. So this is a really cool problem, not just from the paleo, but also from the data assimilation side, right? Because we've got these funky, noisy data, and then this problem where we're trying to do this kind of large-scale data assimilation, but then use it to simulate weather features. And I guess I would say too, when I tell my DA friends about this, they say, Dan, we can't simulate hurricanes in the modern. Like, what are you doing? But this is predicated, I think, on this hypothesis that large-scale fields of sea surface temperatures have an imprint on the statistics of short-term variability. And that with this procedure, we can get at a robust signal on weather extremes. Okay, data assimilation and what we're not doing. So often when people think about data assimilation, this is a useful way of thinking about it. And so I'll briefly talk about what it means to do data assimilation. So when we do ensemble data assimilation, we start out with an ensemble of models. And so often these models are the result of some forecast and they have a bunch of little differences, right? And so if you're thinking about numerical weather prediction, maybe you have a cyclone that's in a slightly different place. And so these simulations are representing the chaotic divergence of the physics in this model. And then along comes an observation. And the observation says, well, there's some property in this model that I can tell you something about, right? I can tell you, its best estimate of its value and also its uncertainty. And so how do you use that? Well, you can reach into your simulations and you can sample your models like the data. And so in the paleo world, we call these proxy system models. You're representing the data equivalent within the model. And then you look at how much model disagrees with your observation. And based on that, you can change your model ensemble. You can add what we call increments to improve the fit of the model to observations. And then time marches on and you continue integrating your model forward. And you can, in this case, you have the opportunity to initialize, say, a forecast of the weather at a future time. Okay, so why isn't that the approach that we're taking for right now? There's a couple of reasons. The first is that this kind of like along came a data point doesn't really apply here because of the nature of our observations. They are just because of the limitations of their preservation, their long time averages, right? We think about a sort of statistical quasi-equilibrium climate rather than what the value was on a particular Saturday. And the second point is that this modality of updating a model and then using it to make a forecast, it doesn't really change the long-term behavior of your simulation. It's great for that moment because you're giving the model the best possible starting point. But in the paleo case, where we're trying to correct large-scale biases of our models, it's not enough just to let the model go because the model will drift back to its biased state. Another thing, another option that we have to explore is offline paleo data assimilation. And this has had, it's been a great time for offline DA in the last 10 years. This is a little bit different because you're not running a model. And so you start off with this catalog of states and you fit your data to it in the least squares sense. And they can give you a best estimate in this least squares sense of past climate. However, it doesn't do a couple of things. First of all, it's a weighted sum of different model states. And there's no guarantee, especially for these big perturbations that we're thinking about, that a linearly weighted combination of model states is actually consistent with model physics. Also, once we get an offline DA solution, it's not clear for our particular purposes how to translate that into a high resolution CESM. So our goal for this project is to change a coupled CESM configuration to be consistent with the proxy data we have within their uncertainties by changing the parameters and the boundary conditions or other persistent changes to the model tendencies. So we don't want to just initialize the model and then let it go. We really want to change it such that when we run it for a long time, we are recovering a climatology that's consistent with the data. Okay, so now I'll tell you what we've tried so far. So we have at our disposal not just the numerical weather prediction, but also a host of other things from modern data assimilation literature. This one has seemed kind of important so far, which is that we don't want to just, so Feng uses this language that I love, every time we assimilate the observations, if we assimilate them once, we're basically eating the whole pizza. And that's great, but it doesn't allow us to probe parameter space in a kind of iterative way. And so one of the techniques that we're borrowing, and this is, I guess, into the jargon weeds here a little bit, but it's called multiple data assimilation or ensemble Kalman inversion. These are approaches that let us sample the data multiple times, such that even though they represent long-term averages, we can iteratively kind of traverse parameter space. So armed with that knowledge, our initial thought with this project is that we would actually frame it as a parameter estimation. We would say, okay, we run these models and we know that there are things that are poorly constrained, right? Like cloud physics, how vegetation and aerosols are treated, the concentration of greenhouse gases. So we could vary these things systematically. And then the workflow we proposed was to borrow this low resolution ensemble and then to run the model forward with this range of parameter values, see how they fit the data, and then repeat. So basically refining our estimate of the parameter space in which the model should be run to best fit the data. I will note that we're not using orbital forcings here, and that's a deliberate choice. It can give us spread, right? It can make our model simulations different, but we thought it would be kind of nonsensical to say, oh, well, you know, in order to fit the Cretaceous, you just need to change the precession to some fixed value, right? Because these things are changing in time. But we ran into problems with this, and they're mostly technical problems. The fact is that I hoped we could get away with short integration times, but you actually need to run the model for thousands of years to equilibrate even the surface ocean temperatures to CO2. At least that's what Feng found with some experiments. For some of these perturbed physics experiments, you actually need to retune the model by hand. And both of these are problems because we're running large ensembles of these things to do data simulation. So we're thinking about relatively low res coupled CESM, but if you're running 40 copies of the model for 1,000 years, that becomes prohibitive. And then the final piece of this was, well, we can tune the parameters for low res CESM, but then what's going to happen when we run the weather model? And so that added another level of uncertainty for us. So in the past few months, we've evolved to a new approach that's trying to sidestep some of those challenges. And it relies on the approach of ocean temperature restoring or relaxation. In effect, we're adding a tendency term to the evolution of upper ocean temperature that basically says, I would like to restore ocean temperature, this x by x of t, to some climatological value that I'm just writing as mu. This has a couple of advantages. We expect it to be robust to changes in resolution. It has a disadvantage that it can suppress the coupling and variability. And I'll show an example of what that looks like. So the workflow that we're looking at now is, okay, we have this initial ensemble of all these different parameter values, and they generate different upper ocean temperature patterns. So then we're going to take those patterns and relax our ensemble of models to them, and then do this kind of iterative approach. Compute how well the model fits the observations, and then iterate. So here, instead of fitting two parameters, our kind of unknown is this upper ocean temperature pattern to which we need to relax the model. And so when we evolve this forward to the weather model, that's how we're going to change the model to fundamentally change its tendency is to keep this relaxation. So we've kind of come up with this iteration. Another thing that we can explore is just to relax to the offline solution, of course, we can lose some of the coupling along the way. Okay, so I'll now just show a couple of examples. So Feng has done some nice work implementing this within the POP ocean model. And so here he's showing two simulations, one at 3 times CO2 in the Miocene and one at 1.5 times CO2. And by implementing an upper ocean temperature restoring, he can get this 1.5 CO2 simulation to look very close to the 3 times CO2. So that's a demonstration that the mechanics of the model are working. The downside of this is that at every time you are trying to relax, and that can dampen variability. And so this is in one of Feng's experiments, he had a target or a baseline, sort of a standard time series of the 1.5 CO2 shown in black, and a target time series in red here. And so as we increase the power of the restoring, and that's fixed by this restoring time scale, you can see that we get closer and closer to the mean, but we're also suppressing some of the interannual variability. So this is one of the things we're going to have to work on, is finding a compromise that helps us match the mean represented by our observations, but also does not suppress too much of the variability. I'm running out of time, so I'll just mention briefly here a couple of other things we're interested in. The restoring is great. It's not, I feel like it's not leveraging all of the tools that we have for data assimilation. And so there is a literature in the modern DA world about formally estimating forecast biases. And so we're interested in exploring this and thinking about short-term variability in the model as an estimate of its long-term, as a noisy estimate of its long-term mean. Another thing that Feng especially is very interested in is thinking about mitigating model biases by basically limiting the spatial or restricting the spatial imprint of how we ingest the data. So we want to assimilate observations, but maybe we don't want to have too large of a bias, and localization can help with that. So yeah, I'll leave these conclusions and discussion points, and really welcome any feedback. Thank you.
Okay, great. Yeah, thanks. Nice talk, Dan. Questions, either in the room or online? Yeah, Vince.
Hey, hopefully you can hear me. Fun talk, Dan. One question I have on the relaxation, and I maybe just kind of missed this because it's a new concept for me, but for the relaxation, I think you were relaxing to climatology. Is the idea to do that with data assimilation and proxy data somehow? I wasn't quite sure what the connection was between the relaxation and the assimilation of proxy data. So wondering if you could, if I'm missing something on that front. Thanks.
Yeah, thank you. It's a great question. It's a little subtle, so thank you for asking. The approach that we're taking is we are going to relax to a field. And that's how we're going to change the model tendency. And so what field should we relax to? And so we start off with a bunch of different prior fields, and we're not going to relax them exactly, right? So if you set the relaxation timescale just to 0, then you will completely recover this SST field that you are trying to restore to. But as you go to longer and longer timescales, you're going to get a compromise between the variability that the model wants to have and this target fields that you have. And so we are saying, okay, that's the compromise we need. So what is the target field? So that is the thing we are solving for. So we take a target field, we run an ensemble of models with an ensemble of different target fields, we compute model data misfits, and then we update these target fields based on those model data misfits. So it has a flavor of parameter estimation to it.
Cool, thanks. That makes more sense. Appreciate it.
Thanks, Vince.
Great. Other questions?
We have a question in the room.
I was wondering, there's this large data gap in the Southern Hemisphere. How are you guys going to address that?
It's a great question. We don't have an easy answer for it.
Okay.
So in practice, I think one of the things that this gets to is that with data assimilation, we would like to provide a solution, and we'd also like to provide some uncertainty. And we do get an estimate of uncertainty from the ensemble spread. And so something that we expect to see is the ensemble spread to be much larger in the Southern Ocean than in the rest of the ocean. But there's no silver bullet for that. We just don't have the odds.
Yeah. But I guess my question was, do you really think this data assimilation, will improve your analysis of warm climates? Considering that half the world, there's no data.
Well, I think one of the reasons we can be optimistic, and one of the reasons that data assimilation is really well suited to paleoclimate, is because it's a data limited problem, no matter what time frame you're looking at. And so you are trying to connect, you have, let's say you have just 2 values in a particular basin, and you're interested in a large scale feature. You could take the average of those 2 values, but that's leaving on the table the fact that we have information about how sea surface temperatures vary in space. Even at these time periods, we expect there to be large scale gyre circulations that can help us make a more sensible large scale map of these things. So that's kind of the intuition behind it, is a physically informed spreading of information. And then another thing that we can do is to ask the question you did in an objective way, and we could sample a pretend world the way we have and try to reconstruct it and see how poorly we do. And so the answer may yet be no, but we have reasons to think it should help.
That's a cool and very ambitious project, because you're going from something very difficult, which is, trying to improve paleosimulations, to go all the way to high res and cyclones and atmospheric rivers. So it's great.
Thanks.
Very cool. All right, thanks. So we're a couple minutes behind, so I guess we should probably move on to our break. But I think we can just go ahead and reconvene at the scheduled time of 2:20. Does that sound?
Yeah, sounds good.
Great. Thanks, everybody.
Last. Okay. So our first talk is by Samantha Stevenson from University of California, Santa Barbara. She will be talking about volcanic effects on the last millennium climate. Samantha?
Great. Yeah, can you hear me and see my slides?
Yeah, great.
Should be in presenter mode now, I hope.
Yes.
Okay, great. Yeah, so thanks for having me. I'm going to talk about 2 projects that are ongoing in my group right now. So that's why there's a long list of co-authors. So they're on several different projects. But yeah, I wanted to highlight the work of Yingying Feng, who is a postdoc with me, and Callie Flieger, who's a PhD student. And they're both kind of working on this idea of volcanic influences on last millennium climate. Okay, so just to orient us to last millennium stuff and volcanoes. So these are generally accepted to be the largest influence on the climate of the last millennium. Of course, excluding anthropogenic activities more recently. But they're a really interesting test case for understanding the dynamics of perturbed climate responses. So what I'm showing here is just a time series of the volcanic sulfate estimates from a recent ice core reconstruction. And so they have like what they call bipolar and unipolar events. So the details aren't too important right now, but what I wanted to highlight is that there are large volcanic eruptions which have happened over the course of the last millennium, which are larger than anything we've seen in the observational record. And the magnitude of those volcanic eruptions is not always super well constrained. Right, so the red and blue bars on the top portion of the graph are from the more recent reconstruction by Michael Sigel et al. And then the green bars down below are the differences between that reconstruction and the older ones by Chow Chow Gao et al. In 2008, which was the one we used for the last millennium ensemble. Right, and so generally they agree fairly well for the smaller eruptions, but particularly for some of the largest events in the last millennium, there are substantial uncertainties in the magnitudes of those events. So if you look at like the 1257 Somalos eruption, for instance, there's like a 50% discrepancy between these 2 ice core derived reconstructions. So there's uncertainties in many aspects of the characteristics of these events, and that makes it kind of difficult to understand how well models are performing at simulating them, right? And this comes up in various contexts. One of the kind of hot topics in last millennium volcano work is whether or not there's a ENSO response to volcanic eruptions. right? So in the CESM1 and most other climate models, I would say there's an El Nino-like response to large volcanic eruptions. So the left-hand plot there is just some work that we did on the LME, Last Millennium Ensemble, showing a composite after it's like the DJF that's roughly 18 months after all large eruptions over the last millennium. And this is robust to the choice of event and most other properties of these eruptions in the CESM. Okay, so it really wants to El Nino the winter after an eruption. But it's not clear whether or not that's true in the real world. Right, so there was a paper that came out in 2020, that's what's shown on the right, based on work of coral-derived work from Palmyra, which is an atoll in the Central Pacific. And they built composites of the coral Delta 18O anomaly, which in Palmyra is a combination of temperature and hydrologic impacts. And that's what's shown in the gray envelope and the black line with the dots on it. Those are the coral records and the range of the coral records, and found that the anomalies there are statistically insignificant. Right? And then the other lines are anomalies derived from climate models at that particular location. Right? So it's a little different than the map, of course, because it's one spot. Right? So it's one location. It's in the real world, we don't have as many realizations of volcanic eruptions as we do in something like an ensemble of models. So it's still, I would say, a little unclear as to exactly how well the model and the proxies should match. But what we can do to try to resolve some of these issues is to say, okay, we're going to try to build sensitivity tests to see whether or not some of the things that we know are like uncertain or incorrect in the models could have an influence on the conclusions that you would draw with regards to the ENSO response. So this is one of the things we're working on right now. So the results I'm going to show are somewhat preliminary. I don't have definite answers yet, but we are trying to take the 1258, in the CESM, it happened in 1258. This large Somalis eruption happened in Indonesia. It's the biggest one over the last millennium. And we built some sensitivity experiments in the isotope-enabled CESM1. So this is the same model configuration which was used for the last millennium ensemble, the same forcing data set, but to simulate the uncertainty in between the older and the more recent ice core reconstructions. What I did was I took the initial Gao forcing data set for that eruption and then scaled it by either 75% or 50%. So that like the 50% seems to be kind of the upper bounds of the interforcing data set differences that we're seeing for that event. So it kind of says, all right, if the CESM is for some reason overestimating the response to volcanoes, such that it's like El Ninoing more than it should be, we could maybe compensate for that by dialing down the magnitude of the volcano itself in the model. So we're looking at size uncertainty, as well as seasonal uncertainty, right? So there's also some questions as to when within the calendar year some of these events happened. So for some of them we know, right, because there's historical evidence. For some of them we don't, and we have to rely on kind of other things like geological indications or straight up just picking something. And so like this is an approach that we used in previous work where we actually like generated forcing data sets that are appropriate for eruptions that happen in 4 different calendar months. Okay, so in this way we can probe both the influences of eruption size and eruption season on the subsequent evolution of ENSO. Okay, so yeah, these plots I just showed you are the aerosol mass mixing ratio from the forcing data set. So what does this do? Well, we're still exploring this, right? But as far as we can tell, both the season and the size seem to have an influence on the ENSO response. So this is pretty interesting. So what I'm showing here is the Nino 3.4 Central Equatorial Pacific sea surface temperature anomaly. Okay, so 0 is normal, positive is El Nino-like, and negative is La Nina-like. And then the vertical colored lines show the starting month of the volcanic eruption in each of the ensembles. Right, and so this is for the eruption at 100% scaling. So it's kind of like this is how big we thought it was to begin with, and this is what happens when you change the season. Okay, so these are new simulations with the isotope-enabled CESM, and there are interesting seasonal differences. which I kind of wasn't expecting based on previous work. But in this ensemble, we ran 5 members for each eruption season. And we're actually seeing that there's a significant difference particularly between the July and the October cases. So when the eruption occurs in July, you see an initial cooling, and then an El Nino, right, which happens in the winter of 1259 or so, and then a La Nina-like response. That's kind of generally true for all of the seasons, but that El Nino is much weaker for the July eruption case and is much larger in the October case, which I'm guessing has something to do with the known seasonal phase locking of ENSO. But the really kind of weird thing that we're trying to figure out right now is this apparent double dip El Nino. Right, so there's an El Nino in the 1259, and then there's another one in 1260, which we had not seen in previous studies with this model. And the La Nina-like response afterwards is not as large. So perhaps there's more heat content being built up in the tropical Pacific in response to the October eruptions. And there could also be, a small number of statistics going on. So we're considering whether or not we need to rerun additional ensemble members. But there's some indications that the season in which the eruption happens can affect the evolution of ENSO subsequently. And then I said size also matters. So here is that same plot that I just showed you on the top, and then the corresponding plot for Nino 3.4 SST anomaly for the 50% scaled case. So if Samalas is actually much weaker than we thought it was, here's what CESM says should have happened instead. And you still see a substantial offset between the July and October cases, but that double dip behavior of the El Nino after the eruption seems to not quite disappear. There's like I don't know, there's something going on there, but it's not as large. And the La Nina response is not as large either. So it does seem like the magnitude of that effect is sensitive to the size of the eruption, which is important because it might be affecting our interpretation of model proxy offsets. So perhaps we do need to worry about these uncertainties in volcanic forcing in order to be sure that we are correctly representing the simulated response to eruptions. Okay, so this is kind of what we have so far on this, but it highlights the importance of volcanic eruptions as a climate perturbation. The other thing that we've been working on with regards to volcanoes is trying to understand not only how they influence the Pacific itself, but how they influence interactions between the Pacific and the Atlantic and Indian Oceans. So here I'm just showing some latitude, longitude bounds of the various index regions that we're using for variability in each of those basins, right? So there's the Nino 3.4. Well, there's all sorts of Nino index regions on the left-hand plot. Nino 3.4 is the one that's kind of in the middle. It's like the dotted one. It's like half green and half blue. And then the tropical North Atlantic and the Indian Ocean Basin mode are the other two. So tropical North Atlantic is just north of the equator, kind of spans most of the longitude of the North Atlantic. And the Indian Ocean Basin mode is that region is designed to isolate essentially the entirety of the Indian Ocean Basin. Okay, so I'm going to briefly explain some of the potential mechanisms. This isn't a comprehensive list because there's all sorts of pathways by which these basins can interact with one another, but just some examples. So there's a tropical and an extratropical pathway by which an El Nino event can induce changes in the tropical Atlantic. This one is the extratropical pathway, where an El Nino like warming in the central and eastern equatorial Pacific leads to a Rossby wave train response in the extratropical atmosphere. So this is kind of equivalent to the PNA or the Pacific North American teleconnection pattern. So you've got these alternating highs and lows. And this tends to lead to an anticyclone forming over the tropical North Atlantic, which then suppresses the strength of trade winds and leads to warming in that region. Okay, so it's kind of a positive relationship between El Nino and the NTA. It's like you can do this similar thing by changing the Walker circulation directly in the tropics. And then in terms of the Pacific Indian Ocean teleconnection, when you get an El Nino event, you can also create warming in the Indian Ocean, right? So it's kind of like the way I think about it is like this two-step pathway where if you have an El Nino, you decrease convection over the maritime continent because it's shifted further east in the Pacific. So the SSTs are cooler than normal in near the Indonesia region, kind of that blue blob that's shown on the figure here, which then tends to create an easterly wind anomaly near the surface and a warming of the Western Indian Ocean and an increase in convection there. And you see corresponding anomalies in the thermocline, right, in the subsurface. So this is equivalent to a warm phase of the Indian Ocean dipole. And then what happens is that warming in the kind of southwestern Indian Ocean can create what they call a C-shaped wind anomaly pattern in the Western Indian Ocean in the following spring, which then has the tendency to suppress the climatological monsoon circulation in that summer. That's what's shown on the right there is just like a diagram of what like normally happens during the summer monsoon. So those anomalies oppose the wind directions there, which overall leads to a warming of the Indian Ocean following an El Nino event. Right. So these are some of the ways in which these basins can interact dynamically with one another. And what we wanted to do in this study is to say, okay, we have many, many simulations of the last millennium with the CESM as part of this last millennium ensemble. And can we use that to make statistical estimates of long-term variations in interbasin interactions? So just brief validation. So this is work that Yingying is leading. If you look at just the regression patterns of SST onto the Nino 3.4 anomaly in the LME versus observations, the model is doing roughly the right thing, as well as models typically do. So we get El Nino-like warming in the Eastern Pacific and cooling over the Western Pacific, right, like I just explained. The spatial structure in the Indian Ocean does have some differences relative to observations, so it tends to overestimate this dipole-like structure in the Indian Ocean. And it doesn't quite get as widespread warming across the Indian Ocean basin in the peak of the El Nino. But, we're working with the tool that we have, and we think that it's relatively reasonable in terms of the structure of interbasin interactions overall. Okay, so, sorry?
2 minutes.
Oh, perfect. All right, I'm almost done. Yeah, so we used the LME to do some longer term analyses of how these interbasin interactions have varied through time. So this is a running correlation between the different basin indices over an 11-year running window. And then the vertical bars are the volcanic eruptions over the last millennium, okay? So you see that there's a lot of internal variability, and there is some indication that there are spikes that are associated with volcanic eruptions, right? In particular, the correlations seem to go down. And yeah, so we said, okay, can we quantify that a little bit more? If you then composite the values of those correlation coefficients in the control simulation in the LME, and then in the 11-year running windows immediately following the eruptions, and we classified them according to hemisphere, but it doesn't seem to matter too much exactly where the eruption took place. But in all cases, you can see that the correlation coefficient magnitude decreases following strong volcanic eruptions. So, or in other words, eruptions seem to decrease the strength of interbasin interactions pretty systematically in this model. And we're still working on the details of the mechanisms, but it seems to relate to an amplification of individual variability in the Atlantic and Indian Oceans as a result of volcanic eruptions. So here, these PDFs are showing just the variance of the 3 basin indices. So as you can see, ENSO doesn't really respond that much after eruptions relative to the overall distribution. But the Atlantic, so the TNA and the IOB, the Indian Ocean, both have amplified variability immediately after eruptions. So we think that, and in the paper we discussed this more, yeah, we think that when you have larger variability in the Atlantic and the Indian Ocean, the relative impact of ENSO is overall lower. And so we think that that's what's going on in response to these eruptions. But we're working on constructing some sensitivity experiments using CESM to kind of verify the relative importance of aerosol forcing and SST changes and try to understand the mechanisms a little more. Okay, So yeah, these are my basic conclusions, right? So the characteristics of volcanic eruptions do seem to have an influence on the subsequent ENSO response in ways that seem kind of complicated and may relate to the initial conditions at the time of the eruption as well. And volcanoes also seem to have a substantial influence on the strength of interbasin interactions in a negative way or negative direction, which seems like it results from just amplifying the Atlantic and the Indian Ocean variability individually. But in general, what I think is the main takeaway is that if we want to understand the dynamics of these volcanic climate impacts and be confident that we're correctly representing these in models, we really need to have good constraints on the properties of the eruptions themselves in order to put that into the model appropriately. So yeah, that's all I have. Hopefully I didn't run over time too much, and happy to take questions if there's time.
And maybe time for one quick question. John.
Great talk, Sam. Again, I'm not familiar with the literature. I'm wondering whether it's worth doing some flux correction runs, whether it's feasible, because we know the model have a big bias in the tropics.
Yeah, I thought of doing that. That could be interesting. Yeah, I'd certainly wonder. I guess you're talking about like flux correcting the climatology, right?
Yeah, exactly.
Yeah, yeah, we just hadn't tried that yet, but that'd be really interesting to see if it matters. I agree. Yeah.
Any other questions? I have a quick one. So, Sam, have you tested removing the volcanic forcing and to see if there's an internal variability of that ENSO?
I don't think I quite understand the question. So removing the volcanic forcing to look at what exactly?
You scaled the forcing magnitude, but have you removed it totally? Because people say the El Nino is caused by volcanism, but when you reduce the magnitude, you still get that response.
Yeah, I mean, if I'm understanding you correctly, we can do this in the LME framework because we have simulations which just don't include volcanic eruptions at all, right? And we did that back in 2016. Like if you look at the relative frequencies of El Nino occurrence after eruptions, it's really significantly increased relative to the just occurrence frequency in a control run. I forget what the numbers are, but it's like 4 times or something more likely. But is that what you mean?
Yeah.
Okay.
Thanks. All right, our next speaker is John. Take it.
Okay. Okay, thank you everyone. Thank you for staying to the end of the meeting. It has been exciting, a lot of exciting talks. So I'm going to give you the last one. It's on some updates on CSM3 and the Paleoclimate Working Group activities. So if you plan to use CSM3 in your research, please get ready for that. The target release date is sometime this summer, although the exact date has not yet been decided. So here is today. The major model parameterization choices have been made. The model developers are tuning the model and incorporating a new climate forcing as we speak. And what's new in CSM3? Here is a non-exhaustive list. In the new atmosphere model, CAM7 uses a spectral element dynamic core with unstructured grid. And we have more vertical levels, 93 versus 32 in CAM6. And you can a lower level configuration with 58 vertical levels is also possible, but it's mostly used for model development. And one thing that is relevant to paleo modeling is that the new atmosphere model has a more accurate radiation. So it corrected a major deficiency in the old radiation scheme. So this is really a good news for paleo modeling. And CSM2 uses a different ocean model than CSM3 uses a different model, ocean model than CSM2. It's MOM6 now. It uses a triple grid with horizontal resolution of about 2/3. And it uses hybrid vertical coordinate in the ocean. And of course, you can choose to run the model in this star as well. On the right, I have a very simple diagram showing you the hybrid coordinate. So you can see in the ocean mix layer, by design, we use Z coordinates. You can design very high vertical resolution there. So you can resolve better represent the mixed layer processes and air-sea interaction. In the interior ocean, we use the isopycnal coordinates. So you only have high resolution when it is needed. So that's the nice feature. And a very important thing oceanographers like this hybrid coordinate is that it reduces spurious mixing. And MOM6 uses natural surface freshwater flux. So the implication for paleo modeling is that we will see much less negative salinity in our paleo simulation. So that's also nice. And in MOM6, the vertical mixing is more closely coupled to wave processes. So by default, we run CSM3 with a wave model coupled in the framework. And the CSM3 will use a new coupling infrastructure. Don't worry about the acronyms here. What's relevant for us is we develop less mapping files, so that's a plus. And also domain files are being replaced with mesh files. So mesh files are used to define the grid, and it's more modern and flexible than the old script files. Due to this model, higher resolution and new capabilities, the model is slower and more expensive. So we get about 10 model years per day, and the cost is 13,000 PE hours per year. And in contrast, for CSM2, we can get around 30 years per day, and the cost is also pretty low. And the Paleoclimate Working Group has been involved in the model development process. And our goal is to evaluate CSM3's climate sensitivity with the last glacial maximum. Here we have a plot showing the equilibrium climate sensitivity against the LGM global cooling. So LGM, global mean temperature, minus the pre-industrial. The dots are results from different generation of CSM models. You see a very nice relationship. So the higher climate sensitivity, the colder the LGM is. And looking at CSM2, it has a high climate sensitivity. The LGM cooling is well outside the proxy suggested range. So we think this model is unrealistic. The high climate sensitivity is a problem. Now we can use Paleo to inform the model parameterizations. And in this case, we identified issues in the macrophysics and ice nucleation. After we correct those deficiencies, we developed the Paleoclimate calibrated configuration, simulates lower climate sensitivity and much more realistic LGM. Then the question becomes, where is CSM3 in this diagram? So we need to set up CSM3 LGM simulation to be able to answer that question. So on the left, we have a very simple illustration of the LGM climate forcing, say lower greenhouse gas concentration in the atmosphere, and the presence of land ice sheets. So the land ice sheets can impact the climate through three pathways. Firstly, you have different albedo and land surface properties that will impact the radiation. And secondly, this topography itself can impact the atmosphere and ocean circulations. Thirdly, the sea level drop can change the ocean bathymetry, circulation, and you also have this shelf exposure as well, which will also impact the radiation. And in our simulation, we incorporate these two major climate forcing, and we use other forcing, use the pre-industrial conditions for simplicity, and they are considered to be secondary anyway. As you can see, that CSM3 is very expensive, so we use previous better equilibrated simulation as an initial condition. And let's dive a little bit into the technical details. So how do we incorporate those climate forcing in greenhouse gas, topography, sea level, and land surface? So greenhouse gas is pretty simple. We find the net CDF file for CAM7. We change the mean value of greenhouse gases. We keep the pre-industrial, seasonal, and the latitudinal variation. For topography, we run the NCAR topo software to generate mean elevation and subgrid scale roughness. And for sea level ocean bathymetry, we need to develop a new MOM6 bathymetry file. And we need to update the land sea mask. In this case, it's a mesh file. And this mesh file is shared by ocean ice right now. The wave model is expensive. So we run the wave model at a coarser resolution, roughly 3 degrees. For that reason, we need a separate mesh file for the wave model. And then to make sure the river runoff is properly rotated to the ocean, so we develop new mapping files between runoff and ocean. So right now, we still need a separate grid file for sea ice. Hopefully, once people update the model code, can use the mesh file directly, so we can have less file to work with. We need a less file to develop. And for the land surface, we need to develop a new land surface data set. And they have updated the method. It's newer and easier to use than CSM2. And we use fixed vegetation type and phenology. And we use the old river transport module for river routing. This is for simplicity. Next, let's look at the results. Left is global mean surface temperature, pre-industrial, and LGM. So the blue line here is the key. So you can see that after 100 years, CSM3 LGM is already 2 degrees C warmer than CSM2 LGM. And importantly, if you look at the top of atmosphere net radiation, so it's positive in CSM3, and it's very negative, -1 in CSM2. So combining all the information together, we think that CSM3 LGM will be much warmer than CSM2. So if we put the result into the diagram, it could be somewhere here. So the LGM will be much more realistic than CSM2. And this may imply that the climate sensitivity will be lower than CSM2 as well. So that's overall very good news for us. And next, let's look at the Atlantic meridional overturning circulation, because this is very important climate feature, determines a lot of large-scale processes. So the blue here is the CSM3 LGM. We are looking at a time series of the maximum AMOC. You can see that it's weakening in this 100-year simulation. It's reaching 10 Sverdrup roughly at the end of the simulation. It's much weaker than the pre-industrial, and it's much weaker than previous like CSM2 LGM as well. We can put this into a little bit historical perspective. The leftmost is CSM3 pre-industrial AMOC and LGM. Next one, CSM4, CSM 1.2, CSM2, and CSM3. So across all those different generations of CSM, you can see that all the models, they can simulate a shallower AMOC. And in terms of CSM3, I think the new thing is that it has the weakest AMOC across all the model versions. So this seems to be something new in CSM3. So we need to further investigate this. Perhaps some ideas, we can run longer simulation to see the response at a longer time scale. And we can also test the sensitivity to different initial conditions. For example, we can use a slightly warmer ocean state from CCSM4 in Brady et al. 2013. And we can also test the role of more realistic LGM tidal energy. The hypothesis here is that for LGM with lower sea level, more tidal energy is dissipated in the interior ocean instead of along the ocean shelves. Because of the stronger tidal mixing, the AMOC might be strengthened for LGM. So in the previous slides I showed you, we use the pre-industrial tidal energy. So we can test a more realistic LGM tidal energy next. And after that, we can configure the model to output the surface mass balance. The goal is to drive offline ice sheets. This is a collaboration with the land ice model working group. And we can prepare for two-way ice sheet climate coupling for LGM. This will be an exciting tool for exciting new science. And I'm very excited to tell you that along this process, we have developed CSM3 recipes. The goal is to document the setup of a challenging paleoclimate simulation like LGM to provide a streamlined Python-based workflow with good notes and references. So hopefully this will motivate and help you to create your own CSM3 simulations for your research. Maybe take a couple minutes more to quickly walk you through some of one notebook. So if you click, it'll take you to the GitHub. If you click CSM3 LGM, and you can see that I have 7 notebooks right now. They are ordered by the workflow. If you work through the 7 notebooks, you will get all the LGM boundary conditions. Maybe, for example, take a quick look at the first notebook. The goal is to create MOM6 bathymetry file for CSM3 LGM. I listed the tools used and add some references. Hopefully they are useful. And this cell is to define the input data and the output data. And along the process, I create a lot of plots trying to show you what's in the netcdf file. And here I list all the 5 steps to create this bathymetry file. And along the way, I generate a lot of plots just to make sure every step is done as intended. In the end, we output the netcdf files for the LGM topography and the mesh file as well. Okay, going back. This is a work in progress, and it's under my GitHub right now. Once it has been finalized, we will publish the suite of notebooks under the NCAR GitHub. And you can share your workflow and analysis code under the GitHub as well. So Paleoclimate Working Group does not have a dedicated liaison, and it is really on us to build community resources, especially for early career researchers who are not familiar with many of the model simulation development process. And what we really don't want to see is that many graduate students, postdocs, they have excellent science ideas, but they got stuck in setting up new paleo simulations. So I think we, as a community, we want to work together to help them. And I also want to bring your attention to our working group website. It's, Esther, Betty, Sophia, and myself, we are working on adding new landing pages for many available simulations. Here is just an example. In the interest of time, I won't go into the details, but on that website, you can see the details of the simulations, also have an FAQ, diagnostic plots. Hopefully it's useful for you. And you can also share your simulation on the website. We will ensure you are properly accredited. And here is a slide trying to summarize some ongoing efforts on Python-based diagnostics. I won't go into any detail, but simply give you an example on using UX array for working with unstructured grid. As you have seen that CSM3, the atmosphere model, ocean model, CIs, land, they are all on unstructured grid right now, so not regular lat-long grid. We can use UX array for visualization. This is an extension to X array. So to use that, you can import UX array. You find the mesh file. It's in the CSM input data folder. And here the data file is my LGM topography. And when you read the data, you provide both the mesh file and the data file. This is your data set. And you can take a look at the variable. It's on unstructured grid. And to make a plot, you simply do ds.phi_s.plot. You get this very nice plot. It's pretty cool. Okay, finally, I want to remind people, please stay connected with more CSM activities. And very, very importantly, the Ocean Model Working Group is putting together this survey to get community input about how Ocean Model Working Group can support our research. So please spend your time and submit your response, fill out this survey. Let oceanographers know how they can help with our paleo science. For example, do you like a 2-degree cheaper and faster ocean model? Do you prefer this regional modeling capability? And do you need help on designing horizontal model grid and vertical coordinates? And would you like tutorials, example materials as well? So please spend maybe a few minutes, fill out this survey when you can find time. And there are many other working group meetings going on after this one. You can check it out on this website. And also the CSM tutorial, the deadline has been extended to February 7th. Please apply if you haven't done so, and please let your colleagues, friends know if you think they might be interested in. And it's exciting that this year is the 70th anniversary of CSM workshop. So please join us and celebrate in the summer. Stay tuned for further information. And I'm probably over time. I will leave the summary here and happy to take questions.
Any questions? Okay, Diane?
Hi, thanks for the great explanation and overview of the CSM3, Zhang. And maybe it's too early to ask this, but then is there no water isotope capability in the CSM3, or is it planned, just not possible right now? And also for the deep time paleoclimate simulations, then if I want water isotope feature in the model, ICSM 1.3 will be still the best option for the next year, I guess.
Yeah. And we have submitted an NSF grant trying to put isotopes back into the latest model version. Hopefully get funded, then we can work on that. So right now we still have to use ICSM 1.3.
Got it. And can I ask you one more question? Is there a plan for the dynamic vegetation for the deep time paleo simulation with the CSM3, or that's still not possible for the paleo simulations?
Sophia, sorry for put you on the spot.
Yeah, Fates is being actively developed. That's kind of gonna be the new dynamic vegetation component that will be incorporated into CSM3 at some point, but not with the scientific release. However, I'm starting to work with Fates in an offline capacity, so that would be an option to do sort of an offline simulation, but not fully coupled yet.
Thank you.
Okay, Betty?
So I just wanted to comment, I know you have it under there, the new Python-based recipes being developed and shared. And you asked the community to also share what they are developing. But the other thing that'd be really useful is graduate students, their best studies are where they don't have to spend years setting up a simulation as their control. Let's say, I don't know, Permian, just I'm looking at someone. But if you finish one of these simulations, it would be really, really great. And we can help you with the post-processing to make those available so that a student then can do a interesting sensitivity study off that simulation. So
Yeah.
we've been trying to do that. We have like LGM, Pliocene and such, but there may be others that time periods, I don't know, Jurassic, let's say. It'd be really great to share those with the community fairly quickly just because the model changes so much. But we keep old versions of the models, but there's a lot of push not to keep really old versions of models because they're hard to keep up to date on our new systems and new compilers. So.
Joseph?
Yeah, so great, thanks for a good talk. I was curious if CSM3 is going to support older versions of CAM, if you wanted sort of like the new ocean, but not so much the new atmosphere, because it seems expensive.
Yeah, I think CSM is doing a great job in maintaining some of the old physics, especially in the atmosphere. So there's effort trying to maintain Chem 4, Chem 5, Chem 6 physics forward in the future. But that's just the atmosphere component. If you would like to do some simulation, say in coupled configuration, I think it's on your own, or you can work with expert trying to, maybe you need to tune the model a little bit if you want to run coupled.
So is it true, Jean, I thought I read this, that CAM is thinking of not supporting some old dynamical cores like the finite volume?
They are considering that.
Yeah, so Paleo Group might be interested in often use the finite volume, but
yeah. Yeah, but the physics packages are still maintained. Yeah.
Okay, Shixiong. Yeah, go ahead.
Yeah, thanks for the great talk. So I just heard from Betty talking about the thinning volume change, dynamic cores changing in CSM3. So I was wondering, is it like, so if we want to use CSM3 and conducting, let's say, high top atmosphere, some research on that. So, you know, like if we're going to use, I'm working on aerosols, obviously. So I was curious because thinning volume is the key kind of like to apply the sub-stepping technique in kind of our setup. So I was wondering if that the thinning volume, is it being canceled or something, or how is it compatible with CSM3 right now? So just wondering.
It's still in the code repository, meaning that you can still use it for now, but in the long term, I really don't know. I think they just got rid of the old Eulerian transform spec dicore. So it's really a burden to keep a lot of features in the model for them. I guess they are having atmosphere working group meeting early next month, maybe in a couple of weeks. Feel free to join their
got it.
session.
Thanks.
Yeah, I think it's next week, in fact.
Okay.
In fact, we convinced them, others did too, to keep CSM 1.3 supported because it is the only isotope enabled version. They never got isotopes in CSM 2 and it will take a while in CSM 3. And the high-res people use it. That said, CSM 1.2 is no longer supported. CSM 1.3 is close. So please, there are documentation. I think you put it already on the webpage, didn't you, Jean? The difference between 1.3 and 1.2.
Yeah.
They're fairly close, but not exact.
Okay. Thanks, everyone. John, would you like to wrap up?
Jesse, thank you for the comment in the chat. Thank you. And thank you, everyone. We have had a lot of great talks. And I also want to thank our admin team for helping us with organizing the meeting, including Elizabeth, Daniel, and Kaylin. Thank you. Maybe let's conclude the meeting, and hopefully I can see many of you in the summer.
So one more thing, John, the